The solar system provides a steady baseline for comparison because most small bodies follow patterns that have been observed many times. Planets remain bright and predictable. Asteroids reflect sunlight without obvious surrounding clouds. Comets, when they become active, develop diffuse coma and tails in recognizable ways as they warm. Against this background, the phrase behaving unlike any known object carries a specific burden. It does not mean that the object must be strange in an absolute sense. It means that within the limits of measurement, one or more observed properties do not match the usual combinations that define familiar categories. In the outermost region of the inquiry, the focus stays on those categories and on what counts as a real deviation rather than a temporary confusion caused by geometry noise or incomplete data. The outer setting is wide because it begins before the object itself. It begins with how the solar system is observed and how classification is normally done. A known small body is usually described first by its orbit. The orbit determines whether the object belongs to the main asteroid belt, the near-Earth population, the Jupiter family comets, or more distant reservoirs such as the Kuiper belt and the Oort cloud. These categories are not aesthetic labels. They are shorthand for histories and typical behaviors. An asteroid in the main belt is expected to be largely inert at the distances where it resides, though some can show weak activity. A comet on a long-period orbit is expected to become active as it approaches the Sun, often at large distances, if it contains very volatile ices, and more strongly at smaller distances when water ice sublimation becomes efficient. If an object's orbit is unbound, meaning it follows a hyperbolic path relative to the Sun, the object is placed outside the usual bound populations and is often considered an interstellar visitor. Even then, the orbit alone does not dictate appearance. It sets a timeline and a geometry for observation, and it can suggest that the object has not experienced repeated close passes by the Sun. That suggestion matters because repeated heating tends to deplete near-surface volatiles and to build insulating dust layers. A first-time passage or a passage after a very long cold interval can preserve volatile-rich layers and produce activity at unexpected distances. This is a general possibility that the solar system baseline keeps in mind without turning it into a prediction. The second broad descriptor is brightness behavior. For any object seen in reflected sunlight, brightness changes with distance from the Earth and from the Sun, and with the viewing angle that determines how much of the illuminated side is visible. These geometric effects can produce large apparent changes without any intrinsic change in the object. This is why unusual behavior cannot be claimed from brightness alone, unless the brightness departs from what geometry predicts, and unless the departure is confirmed across independent data. A gradual brightening as an object approaches can be entirely ordinary. A brightening that is too rapid for geometry, or a brightening that occurs while distances remain nearly constant, can indicate additional scattered light from dust or a change in effective area. But even then, the possibility of background contamination must be eliminated. A faint object moving across a dense star field can pass close to background stars, temporarily increasing measured brightness. Moonlight or thin cloud can shift calibrations. Survey pipelines can produce biases near detection limits. Therefore, the outer setting treats brightness as a measured quantity that must be tied to method and to uncertainty not as a direct measure of physical novelty. The third broad descriptor is apparent shape. A bare nucleus is effectively a point source in most telescopes. A coma makes the profile broader than nearby stars. A tail introduces a directional extension aligned in ways that can be predicted from sunlight pressure and the solar wind. Known comet behavior usually includes some combination of these: a symmetric or mildly asymmetric coma, and a tail that points roughly away from the sun, sometimes with curvature and sometimes with a narrow ion component. Known asteroid behavior usually lacks these extended features, though a small subset of objects called active asteroids can show dust tails due to impact's rotational shedding or weak sublimation. A claim that 3I Atlas is unlike any known object could refer to a mismatch between orbit and appearance, such as an unbound orbit with an appearance that is unexpectedly inert or unexpectedly active, or it could refer to a shape and tail geometry that do not align with the usual antisolar and orbital directions. Yet the outer setting insists on a careful distinction between an image artifact and a physical structure. Tracking choices can smear the target or the stars. Stacking can create spurious gradients if background subtraction is imperfect. The point spread function can vary with time and across the field. Therefore, unusual shape claims must rest on repeated detection, consistent orientation, and comparison to field stars under similar conditions. A fourth broad descriptor is spectral behavior. Known comets often show gas emission features in certain wavelength ranges and dust continua with slopes that reflect grain properties. Known asteroids show mostly reflected sunlight with broad mineral bands in some cases, especially in the near-infrared. If 3I Atlas shows strong emission features at large distances that could suggest very volatile driven activity or a rich inventory of easily released gases. If it shows a spectrum that is unusually smooth and featureless, that could still be consistent with many surfaces, but it could also reflect low signal or strong processing uncertainty. If it shows absorption bands that are rare among solar system objects, that would require careful verification because telluric absorption from Earth's atmosphere can mimic broad features. In the outer setting, spectroscopy is framed as powerful but demanding. A faint moving target requires long exposures and careful calibration. A single spectrum can be misleading. A consistent set of spectra taken over time with explicit treatment of atmospheric corrections and instrument response is needed before spectral novelty is credible. The outer setting also includes the practical reality of discovery and reporting. A newly announced object often appears in public language before the technical picture is stable. Early orbit solutions can shift as more astrometry is collected. Early brightness estimates can vary between surveys due to different filters and apertures. Early reports of a coma can be driven by low-resolution images or by a transient background gradient. This does not mean that unusual behavior cannot be real. It means that the outer region must first establish the baseline of how confident each measurement is. When an object is at the edge of detectability, small systematic errors can produce large interpretive swings. The outer setting therefore treats claims of unlike any known object as hypotheses that require a checklist of measurement stability, consistent astrometry, repeated calibrated photometry, consistent morphology under different instruments, and spectral evidence with quantified sensitivity. Within this wide context, The solar system provides several known ways for an object to appear unusual without being fundamentally unprecedented. An impact can create a dust cloud and a tail from an asteroid. Rotational spin-up can cause mass shedding and produce a transient coma-like envelope. A volatile rich comet can become active at large distances, creating a coma earlier than expected for water-driven activity. An object with very low reflectivity can appear unexpectedly faint for its size, while an object with high reflectivity can appear unexpectedly bright. Phase angle effects can produce brightness surges that mimic outbursts. None of these are rare in principle, but the particular combination of orbit brightness, trend morphology, and spectra can still be uncommon. The outer setting therefore focuses on combinations rather than on single traits. An object that is unbound and shows a long-lasting dust tail with strong gas lines might be rare, but still understandable in known physics. An object that shows strong non-gravitational acceleration without detectable gas lines might suggest either unusual outgassing species measurement bias or an unexpectedly low mass. An object that shows a tail pointing in an unexpected direction could be influenced by projection by variable solar wind or by a dust trail aligned with its orbit, rather than by an exotic force. Each possibility exists within known frameworks, and the role of the outer region is to keep those frameworks in view while the evidence is still forming. The project title centers the tone of the inquiry without forcing the conclusion. 3I Atlas is behaving unlike any known object, is treated as a question about evidence thresholds. The outer setting begins by defining what known means operationally. It means categories built from repeated observations, bound or unbound orbits, inert or active appearance. Dust-dominated or gas-dominated coma tails aligned with antisolar and orbital directions. Spectral continua shaped by reflected sunlight, and emission features shaped by molecular physics. It also means known measurement behaviors, how noise appears, how backgrounds contaminate, how calibration drifts, and how early interpretations can change as data improves. In this outer region, the object is approached first as a moving point embedded in a bright and imperfect sky, and the claim of uniqueness is held in suspense until the baseline is firm. Only after that baseline is secure can attention move inward from the general solar system context to the specific track and measurements of 3I Atlas itself, where the first concrete comparisons to known populations can be made with the caution that the data demands and with the steadiness that the format requires. From the wide solar system baseline, the next outer region narrows to the earliest phase of contact between observers and the object discovery and initial tracking. In this region, the behavior that later appears unusual often begins as a simple problem of detection and confirmation. A survey camera scans the sky and records repeated images. Software compares these images to earlier frames and to star catalogs searching for points of light that move relative to the fixed star field. A candidate is flagged when its motion and brightness are consistent with a solar system object rather than with an artifact. Yet in the first hours and days after detection, many uncertainties remain. The object may be near the sensitivity limit. Its position may be measured with modest precision. Its brightness may be uncertain due to background seeing and filter differences. Therefore, the first steps are structured to turn a candidate into a tracked object with a stable identity. Initial confirmation usually requires follow-up images from the same facility or from others. The candidate must be found again at a predicted position. This prediction uses a preliminary motion vector derived from early detections. At first, the prediction may be crude. A small error in the motion vector can place the target outside the camera's field in the next attempt. This is why early follow-up is often urgent. The longer the time between observations, the more the uncertainty expands along the sky. Once the object is recovered over multiple nights, orbit fitting begins in earnest. Orbit fitting transforms a list of sky positions and times into a trajectory around the Sun. At this stage, the orbit is not yet a final shape. It is a family of possibilities. Small changes in the data can change whether the best fit is a very stretched ellipse or a hyperbola. This distinction matters because it influences how the object is framed, but it can be ambiguous until the observation arc is long enough to constrain it. During initial tracking, the geometry is often unfavorable. Survey images are optimized for coverage, not for deep signal on a single target. Exposure times are limited to avoid star trailing as the telescope scans. For a faint object, this means each detection may have low signal to noise. Low signal to noise increases centroid uncertainty, which affects orbit fitting. It also increases brightness uncertainty, which affects early claims about brightening or fading. Therefore, one of the first improvements in the tracking phase is to obtain deeper, targeted observations. A dedicated telescope points at the predicted location and tracks the target, taking longer or repeated exposures. This increases signal to noise and improves both astrometry and photometry. It also allows the first careful checks of whether the target is a clean point source or shows any hint of extension. The early brightness record is often the origin of phrases like behaving unlike known objects. A discovery survey reports a magnitude in its own filter, often with a large uncertainty. Another facility reports a slightly different magnitude. The difference can reflect real change, but it can also reflect filter differences and calibration differences. Surveys often use broad filters that do not match standard photometric systems perfectly. If the object has an unusual color, the conversion to standard magnitudes can be biased. In addition, early measurements often use fixed apertures that may include different fractions of any diffuse coma if present. A small coma can make a moving object appear slightly fuzzier. This can reduce peak brightness while increasing total brightness in a larger aperture. If different pipelines use different apertures or different background subtraction methods, brightness estimates can differ. In this region, a disciplined interpretation treats early brightness as provisional and focuses on building a consistent light curve with explicit method. Astrometry, in the early phase, also has traps. A faint object's centroid can be pulled by noise by nearby stars or by asymmetric extension. If the object has even a weak coma with a sunward or tailward asymmetry, the brightest point can be offset from the nucleus. This photocenter offset can bias measured positions. When orbit fitting uses those positions, it can produce residual patterns that appear to require non-gravitational acceleration, even when the true cause is centroid bias. Therefore, in the initial tracking phase, it is important to assess morphology and to measure positions in a way that is robust. High-resolution imaging can help, but it may not be immediately available. As a result, orbit solutions can change as better data arrives. This is not a failure. It is the normal correction of early uncertainty. The motion across the sky in the early phase provides the first concrete signal of the object's orbit class. If the object is close to the Earth, its apparent motion may be fast, and its parallax may be measurable from different observatories. If it is far, its motion may be slow and its parallax small. The combination of apparent motion and brightness can be misleading at first. A distant, moderately large object can be faint and slow. A closer, smaller object can be brighter and faster. Without a good distance estimate, these can be confused. This is why early orbit solutions are essential. They provide a first estimate of distance and heliocentric distance, which then anchors the interpretation of brightness. If 3I Atlas is claimed to be unusual early on, part of that claim may trace to a mismatch between apparent brightness and expected size at a given distance, or to a motion that suggests an unbound orbit. Yet both are sensitive to the earliest data quality. During this phase, the object's name becomes formalized. A designation like 3I Atlas links it to the survey or project that discovered it and to the classification system that tracks such bodies. The name does not create the physics. It creates a reference that allows the community to coordinate. Once a designation is assigned, many telescopes can point at the object, and data can accumulate rapidly. This can transform the story from a few survey detections into a multi-instrument campaign. The early tracking region is therefore a transition from scarcity of data to abundance. The pace of data accumulation can be high. With each new night, the orbit fit improves. With each new image, the brightness curve becomes less noisy. With each deeper stack, the search for extension gains sensitivity. Claims of unusual behavior often sharpen or soften in this process. A preliminary orbit that looks strongly hyperbolic may become less extreme or more extreme as uncertainties shrink. A preliminary brightening trend may flatten when calibration is harmonized. A preliminary report of fuzziness may vanish when a point spread function comparison shows the profile matches stars, or it may strengthen when repeated deep images show consistent excess. A preliminary spectral hint may disappear as telluric correction improves, or it may become robust with higher signal. In this region, the correct stance is patient. The early phase is designed to eliminate false anomalies and to reveal real ones. There is also a practical reason why early interpretations can feel dramatic. The object's properties are often described relative to known objects, but the comparison set depends on which properties are reliable. Early on orbit can be uncertain, brightness can be uncertain, and morphology can be uncertain. The mind seeks a category anyway. It chooses asteroid, comet, interstellar visitor, or something else. When later data shows that the chosen category does not fit neatly, the language of unlike known objects emerges. Yet often the true situation is that the object is being measured more accurately than before, and the comparisons are becoming more precise. The object may sit at the edge of several categories, or it may combine traits that are individually known but rarely seen together. By the end of the initial tracking region, the essential outputs are clear and concrete. The orbit is refined enough to predict positions reliably over days and weeks. The heliocentric and geocentric distances are constrained well enough to model geometric brightness changes. The apparent motion is known well enough to plan exposures and tracking. A baseline of calibrated photometry begins to form. A first assessment of point-like versus extended appearance is made. These outputs then support the next inward step, a closer look at the sky geometry and visibility conditions that shape the observations, because even with good tracking, the interpretive weight of any anomaly depends on whether the object is being observed in conditions that allow subtle features to be trusted. With discovery and initial tracking established, the next outer region focuses on sky geometry and visibility, because many apparent anomalies are created or erased by changes in viewing conditions. In this region, the object is still treated primarily as a target in the sky rather than as a physical body. The question is how the Earth's position, rotation, and atmosphere shape what can be measured about 3I Atlas, and how a claim of unusual behavior must be filtered through these constraints. A moving object does not only change its distance, it changes its position relative to the Sun, the Moon, the Milky Way, and the horizon of each observatory. Each change can alter signal strength, background noise, and the reliability of calibration, and therefore each can influence whether the object seems to deviate from known patterns. A first geometric variable is elongation, the angle between the object and the Sun, as seen from Earth. When elongation is small, the object lies close to the Sun in the sky and is difficult to observe because of twilight and glare. Observations must be made near dawn or dusk through thicker air, which increases atmospheric extinction and turbulence. The sky is brighter, raising background noise. Under these conditions, faint comet and tails are harder to detect, and photometric calibration is more fragile. A rise in brightness measured under twilight conditions may not match measurements made under dark conditions, and the discrepancy can appear like an anomaly. As elongation increases, the object moves farther from the Sun in the sky, becomes accessible in darker hours, and can be observed at higher altitude. This improves sensitivity and stability. Therefore, the same object can appear to change behavior simply because its observational circumstances improve. A date that marks an increase in elongation can correspond to a sudden increase in the amount of high-quality data, which can make previously hidden features visible. This can be misread as the object turning on, when the more accurate description is the object becoming observable. A second variable is altitude above the horizon. Light passing through the atmosphere is absorbed and scattered. The lower the object is, the more air its light crosses, and the more it is dimmed and distorted. This effect is described by air mass, which increases at lower altitudes. Photometry is corrected for air mass, but the correction depends on atmospheric transparency and on wavelength. If the atmosphere changes during the night, or if the object is observed at very different air masses on different nights, small errors in correction can create apparent changes in brightness and color. Morphology is also affected. Seeing the blurring caused by turbulence is generally worse at low altitude. A point source can look broader. A faint halo can become undetectable. Therefore, a claim that 3I Atlas has a coma must be tested against seeing conditions and against the behavior of nearby stars in the same frame. A claim that it does not have a coma must also be tested because poor seeing can hide subtle extension. A third variable is phase angle, the angle between the Sun, the object, and the Earth. Phase angle controls which portion of the illuminated side is visible and how light scatters. At small phase angles, many rough surfaces show an opposition effect, a brightening due to reduced shadowing and coherent backscatter. Dust can also show strong forward scattering at certain angles, making a dusty coma or tail appear brighter than expected. At larger phase angles, the visible fraction of the sunlit side can decrease, and certain scattering behaviors change. If the phase angle evolves quickly during the observing window, the object's brightness can change in ways that do not reflect intrinsic activity changes. This is especially relevant for the language of unlike known objects. A brightness surge due to favorable phase angle can look like an outburst. A fading due to phase angle change can look like a shutdown. The outer region approach is to model expected phase behavior and to compare it to the measured light curve. Yet modeling requires assumptions about scattering properties that may not be known. Therefore, phase effects are treated as a plausible confounder, and robust claims require multi-night confirmation and cross-observatory consistency. A fourth variable is background star density. The object moves across the sky sometimes through dense regions of the Milky Way, and sometimes through sparse fields. In dense fields, faint background stars can contaminate photometry, and bright stars can create halos and diffraction spikes that affect background estimation. In sparse fields, background subtraction is cleaner, and coma searches are more sensitive. A moving object can also pass near a background star. If the pass is closed, the object and the star can blend, producing an apparent brightening. As the object moves away, the brightness returns to normal. Without image inspection, this can be mistaken for a transient physical event. Modern pipelines often flag such cases, but they do not catch all. Therefore, any claim of rapid brightening or flickering must be checked against the star field and against the object's path relative to catalogued stars. A fifth variable is the moon. Moonlight raises the sky background and reduces contrast. It also scatters more when there is haze. In moonlit conditions, diffuse features such as comet and tails become harder to detect. Photometric uncertainties rise especially for faint targets. If different reports of the object's behavior come from nights with different moon phases, the differences can be observational rather than physical. This is why coordinated campaigns often prefer dark time. Yet dark time is limited. If a critical date falls under bright moon, observers can still work, but the attainable sensitivity is reduced. In this region, visibility planning is not a minor detail. It is part of the interpretive foundation. A sixth variable is apparent motion across the sky. As the object's apparent rate changes, the exposure time that preserves a sharp image changes. For a fast-moving object, long exposures taken at sidereal tracking smear the object. This reduces peak signal and can complicate coma detection because smearing can mimic a halo. Tracking on the object keeps it sharp, but smears stars, which complicates astrometry and background subtraction. Observers can mitigate this by taking many short exposures and stacking them aligned on the object. Yet stacking requires accurate alignment and consistent background handling. Misalignment can broaden the object and create artificial extension. Therefore, unusual morphology claims must specify the tracking and stacking method. A point source in one reduction can appear extended in another if alignment differs by a fraction of a pixel across many frames. A seventh variable is the filter set used. Different filters sample different wavelength ranges, and the object's spectrum may not be flat. If the object is red, it will appear brighter in redder filters. If measurements from different observatories use different filters and conversions, apparent brightness differences can arise. If an object has emission lines in a particular band, a filter that includes that band can record extra flux. This can create apparent color anomalies. Therefore, in this region, photometry is ideally placed on a common system, using standard stars and transformation equations. When that is not possible, comparisons are made with caution. All these geometric variables combine into an observational cadence that can shape narratives. An object may be first discovered in twilight, then later observed in dark time at higher altitude. The later data can reveal a faint coma that was undetectable earlier. The object may pass into a sparse field, reducing contamination and improving photometry, making variability clearer. The object may reach a phase angle that enhances dust scattering, making a tail more visible. Each of these can be reported as a change in behavior. The outer region response is to treat them as changes in observational sensitivity and geometry. First, then test whether a physical change is required. In the context of 3I Atlas, the phrase "behaving unlike any known object" can therefore be refined into a set of testable conditions. Is the orbit and its class stable under improving astrometry? Are brightness changes consistent across different filters and nights once geometry is modeled? Does any claimed extension persist under varying seeing and stacking methods and align with solar and orbital directions? Do spectral hints survive telluric correction and repeated measurement? These tests are not abstract. They are grounded in the geometry of visibility and the practical limits of observation. By the end of this region, the object is placed into a more stable observational frame. The dates and times when it is observable under the best conditions are identified. The likely sources of contamination and bias are mapped. The relationship between geometry and apparent brightness is recognized as a major driver. This clears the path to move inward again from sky geometry to instrument limits and noise in a more explicit way. Because even under good geometry, the detectors and pipelines impose their own patterns that can create the impression of uniqueness unless they are accounted for with the same steady discipline applied to the sky. With sky geometry and visibility defined, the next outer region focuses on instrument limits and noise because the boundary between ordinary and extraordinary behavior is often drawn by the sensitivity and stability of the measurements. In this region, 3I Atlas is still approached as a faint signal extracted from imperfect data. The purpose is to describe how detectors' optics and reduction pipelines shape the reported properties of a moving object, and how certain forms of noise can mimic the very patterns that are later described as unlike any known object. The emphasis remains practical and measurable. A measurement is not only a number, it is a number produced by a chain of choices. When the object is faint or moving quickly, the influence of those choices increases. A telescope forms an image through an optical system and records it on a detector. The detector converts incoming light into electronic counts. These counts include the object's photons, but also include the sky background photons, thermal electrons generated within the detector, and electronic offsets and noise created during readout. The first limitation is that all measurements are made against a background. For a faint target, the background can be larger than the signal. In such cases, the uncertainty in subtracting the background becomes critical. A small fractional error in the background estimate can produce a large fractional error in the object's brightness. This is why faint object photometry often shows larger scatter, and why sudden apparent changes can occur even when the object is stable. The more diffuse the feature being measured, such as a faint coma, the more vulnerable it is because diffuse light has lower surface brightness and therefore lower contrast against background. The detector itself introduces systematic effects. Bias is a constant offset in the recorded counts that must be subtracted. Dark current is a signal produced by heat that accumulates during exposure. Both vary with detector temperature and can change over time. Flat field variations, the differences in sensitivity from pixel to pixel, remain even after calibration if the flat field reference is imperfect. A moving object samples different pixels over different exposures. If flat field correction is slightly off, the object can appear to vary as it moves across the detector. For fixed stars, this effect can be averaged out by repeated observations, but for a moving object, the pattern can correlate with time, creating an apparent trend. In addition, detectors can have defects such as hot pixels and columns, and can suffer from charge transfer inefficiency that smears signals during readout. These defects can bias centroid measurements for astrometry and can create small asymmetries that look like faint tails or comae if they align with the direction of motion or with detector axes. Optical effects also matter. The point spread function, the effective shape of a point source on the detector, depends on the optics and on atmospheric seeing. It can vary across the field due to aberrations. If the object lies near the edge of the field, its profile may differ from that of comparison stars closer to the center. If the telescope focus drifts, the point spread function broadens. For coma detection, this is critical because the method relies on comparing the target's profile to stars. A slightly defocused star can look like a small coma. A slightly trailed object due to tracking error can look like extension. Therefore, robust coma claims require that the stars in the same local field show a stable profile and that the object is not affected by differential trailing. Tracking and guiding are especially important for fast-moving objects. If the telescope tracks at the sidereal rate a moving object trails, trailing spreads the object's light over more pixels, reducing peak brightness and making centroid estimation harder. If the telescope tracks the object star's trail, complicating astrometry and background modeling, a guiding error can introduce a subtle drift during the exposure, broadening both stars and the object in a direction that can coincide with antisolar or orbital directions by chance. This coincidence can be seductive because it can mimic a physical tail. In this region, the discipline is to test whether any extension remains when exposures are shortened, when tracking is adjusted, and when different nights and different instruments are compared. Reduction pipelines add another layer. Modern surveys use automated pipelines that detect moving objects, measure their positions and brightness, and report them quickly. These pipelines must operate reliably across huge volumes of data, and they use standard assumptions. They may use fixed apertures. They may assume a point source profile. They may not be optimized for a faint object with a weak coma. If an object deviates from these assumptions, the reported magnitudes can be biased. For example, if a weak coma makes the profile broader, A pipeline tuned for point sources may underestimate total brightness because it captures less of the extended light. Another pipeline with a larger aperture may capture more, producing a brighter magnitude. The difference can be misread as variability or as a sudden change when the object transitions between surveys. Therefore, in this region, photometry must be homogenized, placing measurements on a consistent system with consistent apertures or with aperture corrections based on the point spread function. Noise also has statistical structure. Photon noise follows counting statistics. If the object delivers few photons, relative noise is large. Red noise adds an additional floor, especially for short exposures. When many short exposures are stacked, photon noise decreases with the square root of the number of frames. But systematic errors do not necessarily decrease. A residual flat field gradient, a scattered light pattern, or an imperfect background model can persist in the stack, and can even become more visible as random noise is reduced. This is why deep stacks can reveal both real faint coma and false faint gradients. A false gradient can appear as a one-sided halo mimicking asymmetry. To guard against this, observers create control stacks, vary background modeling, and check whether the feature rotates with the sky or remains fixed relative to the detector. A physical coma remains centered on the object regardless of rotation of the field. A detector artifact remains fixed in detector coordinates. This is a key test in this region. Cosmic rays and satellite trails introduce additional transient artifacts. A cosmic ray hit can create a bright pixel or streak that, if coincident with the target location in one frame, can bias the measured brightness upward. A satellite trail can cross the aperture and add extra counts. Automated masking may remove many such events, but not all. The risk increases when the target is faint and the aperture is large because more pixels are included. Therefore, sudden single-point spikes in a light curve are treated with suspicion unless supported by multiple frames and multiple instruments. Spectroscopy has its own limits. A spectrum is sensitive to sky emission lines, which can be strong and variable. If the target is faint, sky subtraction becomes challenging. Residual sky lines can mimic emission features. Telluric absorption from Earth's atmosphere can imprint broad bands that, if not corrected well, can be mistaken for object absorption bands. Instrument response can create artificial slopes. Therefore, claims of unusual spectral features require repeated observations and careful calibration. For a moving target, slit losses can also matter. If the target drifts in the slit due to tracking error, some light is lost, changing the spectrum shape and the measured brightness. An extended coma can also contribute light differently depending on slit orientation. Thus, spectral anomalies can reflect observational setup rather than intrinsic composition. In this region, the meaning of behaving unlike any known object becomes more specific. It can mean that after accounting for instrument limits and noise, the object still shows a pattern that cannot be removed by calibration or method differences. For example, if multiple independent pipelines using different instruments and different nights agree that the object's brightness rises beyond geometric expectation, that would be less likely to be a calibration artifact. If multiple independent high-resolution images show a consistent asymmetric coma aligned with anti-solar direction, that would be less likely to be a tracking artifact. If multiple spectra from different facilities show the same emission features at the same wavelengths that would be less likely to be a sky subtraction residual. The outer region therefore sets a high standard. It demands replication method transparency and explicit uncertainty. By the end of this instrument and noise region, the object is framed as a signal whose credibility depends on how well systematic errors are controlled. The region does not deny unusual behavior. It builds the foundation for claiming it responsibly. Once this foundation is established, the narrative can move inward again to orbit refinement and residual analysis, because the orbit is the one aspect of the object that can be measured with extraordinary precision. Even when the object is faint and subtle differences between predicted and measured positions can provide a clean test for physical forces, provided that the astrometry itself is not biased by the very instrumental and morphological issues described here. With instrument limits and noise accounted for, the next outer region returns to astrometry and orbit refinement, because the orbit is the spine that holds all other interpretations in place. In this region, the behavior of 3I Atlas is assessed through the quiet discipline of positional measurements. The object is treated as a moving point, whose location can be measured with precision that often exceeds what is possible for its brightness or morphology. Orbit refinement is the process of turning thousands of small positional facts into a coherent trajectory, then testing that trajectory against new data as it arrives. When people say an object is behaving unlike any known object, the first stable question here is whether the orbit is itself unlike known classes, and whether the orbit remains stable under increasing data or shifts in ways that suggest unmodeled forces or measurement bias. Orbit fitting begins with a set of observations times sky coordinates and uncertainties. A solver finds the set of orbital parameters that best reproduces those positions under gravitational forces from the Sun and planets. The quality of the fit is evaluated by residuals, the differences between predicted and measured positions. Early in the discovery arc, the residuals can be large and structured because the orbit is poorly constrained. As data accumulates, residuals should shrink and become more random if the model is adequate and the measurement errors are correctly estimated. This is the first sign of stability. A stable orbit is one where adding new data changes the solution only modestly, and where predictions remain reliable. For an object on an unusual trajectory, stability is achieved later than for a typical main belt asteroid, because the object may be far faint and observed over a shorter arc relative to its total path. A key refinement step is improving the star reference frame. Modern astrometry relies on precise star catalogs. If earlier measurements used older catalogs or less accurate reference stars, re-reduction can improve astrometric accuracy. This can shift the orbit solution slightly. For an object with a potentially unbound orbit, small shifts can matter in the computed eccentricity, the parameter that distinguishes a bound ellipse from an unbound hyperbola. If the eccentricity is greater than 1, the orbit is hyperbolic relative to the Sun. Yet because measurements carry uncertainty, an eccentricity just above 1 can sometimes be consistent with a bound orbit once uncertainties are considered. Therefore, in this region, claims of interstellar classification are treated as statistical. The orbit is described with confidence intervals. The question is whether the best fit and its uncertainty range remain comfortably above 1 as data accumulates. If they do, the unbound classification becomes robust. If they do not, the classification remains provisional. Orbit refinement also includes planetary perturbations. The planets, especially Jupiter, can alter comet trajectories. A bound comet can be scattered into a highly eccentric orbit. A near-parabolic comet can become slightly hyperbolic after a planetary encounter. Therefore, an orbit that is hyperbolic at the time of observation does not automatically imply an interstellar origin. A full dynamical analysis can integrate the orbit backward to large distances and test whether the object was unbound before entering the planetary region. This requires accurate initial conditions and an understanding of uncertainties. In this region, the important point is that orbit unusualness must be interpreted in context. An orbit can be unusual because it is truly interstellar, or because it is a solar system object perturbed onto an escape trajectory. The difference is a matter of dynamics and uncertainty, not of appearance. Astrometry for active objects has special challenges. If the object develops a coma, the measured position can shift from the nucleus to the photocenter of the coma. If the coma is asymmetric, the photocenter can shift systematically, creating residuals that look like non-gravitational acceleration or orbit mismatch. This is why orbit refinement in this region is linked to morphology assessment. If the object remains point-like, photocenter bias is less likely. If it becomes extended, especially with a sunward or tailward asymmetry, astrometric positions must be treated with more caution. Some observers use techniques to estimate the nucleus position within a coma by fitting models. Others restrict orbit fitting to measurements made with small apertures or high resolution. Yet each approach has limits. The region therefore emphasizes that orbit residuals must be interpreted alongside knowledge of the object's appearance. Another refinement step involves weighting observations. Not all measurements are equal. Some have higher signal-to-noise and better seeing. Some are taken at high altitude under stable conditions. Others are taken in twilight or near the horizon. Orbit solvers often weight observations by their estimated uncertainties. If uncertainties are underestimated for poor conditions, those observations can pull the fit and create structured residuals. If uncertainties are overestimated, good data may be underused. Therefore, a refined orbit involves iterative adjustment, fit, examine residuals, identify outliers, adjust weights, refit. Outliers can arise from misidentification, from contamination by stars, or from timing errors. A single mistaken measurement can distort early solutions. As more data accumulates, the influence of any one point decreases, and the orbit becomes more stable. In the context of claims of unusual behavior, there is a specific kind of orbit-based anomaly that matters: measurable non-gravitational acceleration. If residuals remain systematic after accounting for measurement issues, a non-gravitational model can be fitted. This often includes radial transverse and normal components relative to the orbital frame. A significant fitted component can indicate outgassing thrust. Yet the same caution applies: an asymmetric coma can bias positions. Therefore, a robust non-gravitational detection requires consistent residual patterns across data sets and ideally confirmation that the object's morphology and photometry indicate activity at the same time. If a non-gravitational acceleration is claimed, While the object appears point-like and shows no gas or dust, the claim demands extra scrutiny because measurement bias becomes a strong alternative explanation. On the other hand, if a non-gravitational acceleration is detected while a coma is present, the detection becomes more plausible, though photocenter bias must still be considered. Orbit refinement also yields practical outputs that shape observation strategy. It provides ephemerides, predicted positions, and velocities on the sky. Accurate ephemerides allow large telescopes with narrow fields to point correctly. This matters because the deepest and most diagnostic observations often come from facilities that cannot search widely. If the orbit is uncertain, such facilities may miss the target or waste time. A stable orbit therefore increases the chance that spectroscopy, high-resolution imaging, and thermal measurements can be obtained. In this way, orbit refinement is not only interpretive, it is enabling. In this region, the orbit can also be used to compute incoming and outgoing asymptotes, the directions from which the object appears to arrive and depart at large distances. For a truly interstellar object, the incoming direction can be compared to the local stellar motion and to known streams of interstellar material. Such comparisons are subtle and do not imply origin from a specific star, but they can place the trajectory in a galactic context. Yet this is still part of orbit analysis, and it depends on having a robust, unbound trajectory. Therefore, it remains a later step contingent on orbit stability. By the end of this region, the orbit becomes a reliable scaffold. The object's path through space is described with quantified uncertainty. The classification as bound or unbound is either strengthened or left provisional with clear boundaries. Any evidence for non-gravitational acceleration is either supported or constrained. The link between astrometric residuals and morphology is made explicit. This prepares the narrative to move inward to brightness trends, because once distance and geometry are known with confidence, the light curve can be compared to expectations more meaningfully. Only then can a claim of unlike any known object based on brightness behavior be evaluated with the restraint that the measurement chain and orbit analysis require. With the orbit refined as a stable scaffold, the next region turns to brightness trends over time, because brightness is the most visible channel through which claims of unusual behavior are often made. In this region, the aim is to separate three overlapping influences: the geometric effects of changing distances, and phase angle, the observational effects of changing conditions and methods, and the physical effects of activity or changing effective area. The object's brightness record becomes a light curve that can be compared against a modeled baseline. Only when that comparison is disciplined can the phrase "behaving unlike any known object" be grounded in something more than surprise. The geometric baseline begins with distance to the Sun and distance to the Earth. As the object approaches the Sun, the sunlight that illuminates it becomes stronger. As it approaches the Earth, the same reflected or emitted light arrives more strongly at the telescope. These effects are multiplicative and can change rapidly if distances change rapidly. With an accurate orbit, the distances as a function of time are known well enough to compute an expected trend for an inert reflector. For a point like nucleus, the expected brightness in reflected light is proportional to the inverse square of the Sun distance times the inverse square of the Earth distance, with additional dependence on phase angle and on scattering properties. In practice, observers often describe the brightness trend in magnitudes and compare it to a power law with respect to heliocentric distance. A purely geometric trend is usually smoother and more predictable than an activity-driven trend. But in real data, the two can blur because phase angle effects can introduce bumps and because scattering properties can vary between objects. Phase angle is particularly important because it can create brightness behavior that looks dramatic. At small phase angles, some surfaces show an opposition surge, a brightening that can be stronger than expected from distance alone. Dust can show strong forward scattering, making a coma or tail appear brighter when the observer is near the scattering direction. If the orbit geometry places the Earth into such an alignment, the object can brighten faster than distance predicts without any increase in material production. For an object that might have a dust component, this effect can be significant. Therefore, in this region, a claim of unexpected brightening must be checked against the evolution of phase angle. The check is not perfect because scattering properties are not known in advance, but the geometry can at least indicate whether a brightness surge coincides with a phase angle regime where surges are plausible. Once geometry is accounted for, the measured light curve is examined for residual behavior. Residual behavior includes deviations from the expected curve, periodic variations, and abrupt changes. Periodic variations can arise from rotation of an irregular nucleus. If the object is elongated or has albedo patches, its projected area and reflectivity change as it spins, producing a repeating pattern. The period can sometimes be extracted from repeated photometry. If the period is stable across nights and across instruments, it becomes a robust property. A stable period is a normal trait of small bodies. Yet a very large amplitude, meaning very large brightness swings, can suggest an extreme shape or a contact binary, though the interpretation is geometry dependent. If the amplitude changes over time, it can reflect changing viewing angle or the growth of a coma that smooths the variations. In this region, rotation is treated as a possible contributor to what looks like unusual variability, especially if the data cadence is sparse and aliases can occur. Abrupt changes in brightness are often the most tempting basis for uniqueness claims. A sudden brightening can be caused by an outburst where gas and dust release increases rapidly. It can also be caused by fragmentation where the object breaks into pieces and the total reflecting area increases. Yet it can also be caused by observational contamination, such as a close pass to a background star or a change in aperture or calibration method between surveys. Therefore, the region's discipline is replication. A real outburst should appear in multiple exposures and preferably in multiple observatories, separated in location and pipeline. It should also be accompanied by morphological changes, such as the emergence of a coma or an increase in extension. A contamination event often appears in one data set and not in another, or appears as a single-point spike with no morphological change. Therefore, the light curve is not interpreted alone. It is cross-checked against images. If the object develops a coma, the brightness record becomes more complex, because different apertures capture different fractions of the coma. An object may appear to brighten simply because observers choose larger apertures as the object becomes easier to measure. Conversely, a pipeline optimized for point sources may miss extended light and underreport brightness as the coma grows. This can create apparent dimming or an odd flattening. In this region, the best practice is to report brightness within fixed physical apertures, when possible converting angular apertures to physical distances at the object using the known distance. This allows brightness to be compared across time in a way that accounts for changing distance. When that is not possible, observers at least report the aperture used and attempt aperture corrections. The goal is to ensure that apparent changes are not artifacts of changing measurement scale. A light curve can also reveal the onset of activity. As a comet approaches the Sun, activity often begins gradually, then increases as more volatile substances sublimate. The brightness then follows a steeper dependence on heliocentric distance than an inert body because the coma adds light. In many comets, the brightness can rise roughly as a power of heliocentric distance, with an exponent that is larger than 2 reflecting increasing production. Yet the exponent varies widely. Some comets brighten slowly, others brighten rapidly. If 3i Atlas shows a brightening rate far steeper than typical comets at a similar distance, this could be taken as unusual. But the region insists on checking whether the object is being compared to the correct population. Long-period comets, first-time visitors, and objects driven by very volatile ices can behave differently from short-period comets. An interstellar visitor, if truly such, could preserve volatiles differently and show activity patterns that are rare in the known sample. Therefore, unusualness is judged by comparison sets that match orbit class and thermal history, as well as distance. Another possibility is unusual fading. Some comets fade unexpectedly if they fragment and disperse, or if their active area becomes sealed by redeposited dust. If the object fades faster than geometry predicts, this could suggest changes in activity or structural disruption. Yet fading can also occur if the object moves into a star-crowded field, where background subtraction becomes harder and brightness is underestimated. It can occur if moonlight rises or if transparency declines. Therefore, fading claims also require careful control. The best evidence for physical fading is a consistent trend across multiple observatories and a correspondence with changes in morphology or spectral signatures. In this region, the phrase "behaving unlike any known object" is therefore translated into specific light curve diagnostics. It could mean a brightening or fading rate inconsistent with geometry and inconsistent with known comet activity patterns. It could mean large amplitude periodicity suggesting an extreme shape. It could mean repeated outbursts not easily explained by observational artifacts. It could mean a mismatch between brightness evolution and the presence or absence of coma or gas lines. Each of these can be tested, but each requires that the light curve be built carefully from calibrated photometry tied to the orbit. By the end of this region, the brightness behavior is no longer a headline. It is a structured record with a modeled baseline and measured residuals. The record supports constrained statements: the object brightens at a certain rate with uncertainty shows, or does not show periodic modulation, within limits exhibits, or does not exhibit abrupt events within the data coverage and shows, or does not show aperture dependence consistent with extended light. These statements then prepare the narrative to move inward again to color and broad spectral slope. Because once brightness trends are understood, color trends can be interpreted more cleanly, and unusual color behavior can be evaluated as a property of the surface and dust, rather than as a side effect of inconsistent photometry. With brightness trends structured against geometry and method, the next region narrows to color and broad spectral slope, because these are the first measurements that speak even indirectly to what the object's light is made of. In this region, the goal is not to assign composition by label. The goal is to describe what color measurements can reliably indicate what they cannot, and how unusual behavior claims can be strengthened or weakened by whether color remains stable, drifts smoothly, or shifts abruptly. Color is a difference between brightness measurements in two filters and broad spectral slope is the way brightness changes across a wider span of wavelengths. Both are sensitive to the mixture of nucleus light and any dust coma light, and both are sensitive to calibration and atmospheric effects. Therefore, as in earlier regions, the focus stays on measurement discipline and on the careful separation of physical signals from observational artifacts. A color measurement begins with two images taken through different filters. The images should be taken close in time because the object can vary in brightness and because atmospheric transparency can change. For a moving object, taking the images close together also ensures that the object remains against a similar background star field, reducing contamination differences. Each image is reduced background subtracted and calibrated to a standard system using stars of known color and brightness. Then the object's magnitudes are compared. The difference is the color index. A redder color index means the object is relatively brighter at longer wavelengths. A bluer index means it is relatively brighter at shorter wavelengths. The first physical interpretation of color is about scattering. Light reflected by a surface or by dust grains is modified by the material's reflectance, which depends on composition, grain size, and texture. Many small bodies show red slopes because their surfaces contain complex organics, or because their grains scatter light in a way that favors longer wavelengths. Dust released from a comet can also show red slopes, and in many cases, coma dust is redder than the nucleus surface because fresh dust grains have different scattering properties and because multiple scattering in a coma can alter the effective slope. Yet there is no single mapping from redness to composition. Different mixtures can produce similar slopes. Grain size effects can mimic compositional effects. Therefore, in this region, redness is treated as a comparative measure. It can place the object within the range of known populations, such as typical comet dust, typical D-type asteroids, or other classes. But it rarely identifies a unique material. Color can also be influenced by phase angle. As the phase angle changes, scattering can change in a wavelength-dependent way. This is called phase reddening when objects become redder at larger phase angles. The effect is seen in some asteroids and can occur in dusty coma as well. If the object's phase angle is evolving, a gradual color drift may be geometric rather than intrinsic. Therefore, color time series must be interpreted alongside geometry. If color changes correlate with phase angle changes in a consistent way, phase effects are plausible. If color changes do not correlate, intrinsic changes become more plausible. But the possibility of calibration drift remains. Calibration is a major challenge, because color is a difference between two numbers. Any systematic error in either band can shift the color. Atmospheric extinction is wavelength dependent, so errors in air mass correction can produce artificial color. Thin clouds can scatter light and can be more effective at shorter wavelengths, producing an artificial reddening. The object's motion can carry it across background stars that have their own colors, contaminating one filter more than another if the star is brighter in one band. Therefore, a robust color claim requires careful star subtraction and consistent calibration stars, and ideally confirmation by independent observers using different instruments. In this region, unusual color behavior is not accepted without such cross-checks. If a coma is present, color becomes a blend. The nucleus contributes a compact signal. The coma contributes extended signal. If the nucleus and coma have different colors, the measured color depends on aperture size. A small aperture may be nucleus-dominated and yield one color. A larger aperture captures more coma and yields another color. This aperture dependence itself can be diagnostic. If color becomes redder with larger apertures, it suggests that the coma dust is redder than the nucleus. If color becomes bluer with larger apertures, it suggests different dust properties or perhaps contamination by gas emissions in one band. Some molecular emissions lie within common photometric bands and can add light in a band, making the color appear bluer or redder depending on which band is affected. Therefore, in this region, aperture dependence and filter choice are important. A claim of an unusual color should specify the filters and apertures used. Broad spectral slope is a generalization of color across more bands or from a spectrum that has been smoothed. A spectrum dominated by reflected sunlight will show solar absorption lines, but the overall shape will reflect the object. Observers often remove the solar spectrum by dividing the object spectrum by a solar analog star spectrum. The result is a reflectance spectrum. The slope of this reflectance spectrum and any broad absorption features are then examined. A featureless red slope is common for many primitive bodies. Broad absorption bands in the near-infrared can indicate minerals or ices, but detection requires high signal and careful telluric correction. In this region, the slope is used as a way to compare 3-eye atlas to known objects. If the slope is extreme compared to typical comet dust or typical asteroids that could support unusualness. If the slope falls within known ranges, it suggests that the object's surface or dust is not dramatically different in broad reflectance properties, even if other behaviors are unusual. Color variability over time can also suggest changing dominance between nucleus and coma. If the object brightens and simultaneously becomes redder in a way that cannot be explained by phase angle, it may suggest increasing dust contribution. If it brightens and becomes bluer, it may suggest gas emission contribution or a different dust size distribution. If it shows abrupt color shifts, it could reflect an outburst that releases a different kind of material, perhaps fresher or finer dust. Yet abrupt shifts can also be caused by poor calibration on a given night. Therefore, in this region, the most credible color changes are those that are smooth and repeatable, or those that coincide with independently confirmed events, such as a morphological outburst. In the context of behaving unlike any known object, color and slope can refine the claim. If the object's behavior is unusual in brightness or motion, but its color is typical of known comet dust, this suggests that whatever is happening may involve familiar materials behaving in an uncommon way. If the color is unusual, perhaps outside the typical range of known comets and asteroids, this suggests that either the surface materials or grain properties may be uncommon. though the statement remains comparative rather than definitive. If the color changes in a way that does not match known phase reddening or typical comet activity evolution, this can add weight to the claim that the object does not fit familiar patterns. Yet the region holds steady on the principle that color is suggestive but not decisive. It is one axis in a multi-axis comparison. By the end of this region, the object's broad spectral character is described in plain terms, whether it is red, neutral, or blue in broad slope, whether that slope remains stable or changes, whether the changes correlate with brightness or with phase angle, and whether aperture dependence indicates different components. This description sets up the next boundary toward physical clues, because once color behavior is established and calibrated, it becomes more meaningful to ask whether extended light is present and how its structure evolves. Color provides hints about dust and gas contributions. Morphology provides the spatial context. Together, they allow the narrative to cross inward from photometric descriptors into the first physical inferences about activity still cautious and still anchored in what the data can support. With brightness and color mapped against geometry and method, the next region marks the first deliberate boundary toward physical clues. This boundary is crossed not by speculation, but by combining multiple observational channels into a single question. Does 3-eye Atlas behave like a passive reflector, or does it show evidence of releasing material into space? Releasing material is the simplest physical distinction between an inert small body and an active one. It can occur through sublimation of volatile ices, through impacts, through rotational shedding, or through other processes. In this region, the task is to describe what counts as evidence for material release and what patterns of evidence are needed to make the claim robust. The phrase behaving unlike any known object is treated as a hypothesis that becomes stronger only when evidence of activity is both consistent and difficult to explain by known confounders. The most direct imaging evidence for material release is extended light around the object, a coma. A coma is not a metaphor. It is scattered sunlight from dust grains, and in some bands, emission from gas. In practical terms, a coma is detected when the object's light profile is broader than that of nearby stars in the same image, and when the excess persists across exposures and nights. The comparison to stars is essential because stars provide the empirical point spread function under the same seeing and optical conditions. If the object matches stars, it is point-like within limits. If it is broader, it may have a coma, but only after ruling out trailing focus errors and stacking artifacts. The region therefore treats coma detection as a statistical statement. It is not enough that the object looks fuzzy once. It must be consistently broader than stars by an amount larger than the measurement scatter. A second imaging evidence is asymmetry. A coma can be symmetric or asymmetric. Asymmetry matters because it often indicates directionality in release or shaping by sunlight and solar wind. An asymmetric coma can show a sunward enhancement, a tailward enhancement, or a fan. Yet asymmetry is also where artifacts hide. Background gradients can create one-sided halos. Residual star trails can create streaks aligned with the direction of motion. Detector effects can create subtle elongations aligned with pixel axes. Therefore, in this region, asymmetry is accepted only when it is stable in object-centered stacks and when its orientation behaves physically, such as remaining aligned with the anti-solar direction, as that direction changes with time. A feature that remains fixed in detector coordinates is likely instrumental. A feature that remains fixed relative to the nucleus and rotates appropriately with the sky is more likely physical. A third evidence is aperture dependence in photometry. If the object has extended light, a larger aperture captures more flux than expected for a point source compared to stars. Measuring the object in multiple apertures can reveal an excess growth curve. If that excess is present, it supports a coma even when visual inspection is ambiguous. This method is sensitive, but it is also vulnerable to background estimation errors and star contamination. Therefore, it must be paired with careful masking and with comparisons to stars. In this region, aperture dependence is used as supporting evidence, not as the sole basis for a coma claim. A fourth evidence comes from tail geometry. Dust tails and ion tails have characteristic alignments relative to the Sun and the orbit. Dust tends to be pushed away from the Sun by sunlight pressure, and to retain orbital memory, producing curved tails that often lie between the anti-solar direction and the projected orbit direction. Ion tails formed from ionized gas tend to align more directly with the anti-solar direction and can show rapid changes due to solar wind variability. If a tail is detected, its orientation can be measured and compared to these expectations. A tail pointing in a direction inconsistent with both anti-solar and orbital vectors could indicate projection effects, an unusual dust release history, or an artifact. Therefore, in this region, tail detection is treated as geometric evidence that must fit within known force frameworks. A tail can still be unusual, but it is unusual in a measurable way, such as having an unexpected curvature evolution or an unexpected brightness distribution, rather than simply being surprising. A fifth evidence is spectral. Gas emission features provide direct proof that molecules are being released and are being excited by sunlight. Broadband photometry can be influenced by gas emissions in certain bands, but spectroscopy can isolate specific features. If emissions are detected consistently at the same wavelengths and are spatially extended around the nucleus, the case for outgassing becomes strong. If no emissions are detected, the case for activity is not eliminated because dust can dominate and because some gases are hard to detect in certain bands. Yet the combination of a coma without gas lines can indicate a dust-rich release, perhaps driven by weak gas or by mechanical ejection. Conversely, gas lines without a visible dust coma can indicate gas-rich outflow with little dust entrainment. In this region, the physical inference depends on the combination of channels rather than on a single measurement. A sixth evidence is dynamical. Non-gravitational acceleration detected in the orbit can indicate asymmetric outgassing thrust. This is powerful because it integrates over-gas release, even when gas is hard to detect spectroscopically. Yet it is also vulnerable to photocenter bias if a coma is asymmetric. Therefore, in this region, a dynamical claim is strongest when it coincides with independent morphological or spectral evidence of activity, and when astrometric methods are designed to reduce photocenter bias. When these evidences are assembled, they form a matrix of possible regimes. A passive reflector regime shows point-like morphology, brightness trends, consistent with geometry, stable color behavior, no gas emission features, and no detected non-gravitational acceleration within limits. An active dust-rich regime shows extended morphology, brightness excess beyond geometry color behavior, consistent with dust contributions, tail structure, aligned in physically meaningful directions, and possibly weak or absent gas lines, depending on sensitivity. An active gas-rich regime shows gas emissions, possible ion tail, and potentially non-gravitational acceleration with a dust coma that may be weak. A mechanical ejection regime, such as impact or rotational shedding, can show dust features without strong gas signatures, often with sudden onset, and then fading as dust disperses. Fragmentation can show abrupt brightening and complex morphology with multiple condensations. In this region, 3I Atlas is positioned within this matrix as the evidence allows without forcing it into a single box prematurely. The phrase "unlike any known object" becomes meaningful here if the object's evidence combination does not map cleanly onto these regimes. For example, if it shows a strong non-gravitational acceleration, but no gas lines and no coma within deep limits, that would be difficult to reconcile with known patterns and would require careful scrutiny of astrometry bias and consideration of unusual outgassing species or physical properties. If it shows a tail geometry that persistently does not align with expected directions and cannot be explained by projection, that would be unusual and would require testing for processing artifacts and for unusual dust dynamics. If it shows repeated sharp brightening events without a corresponding dust envelope, that would be unusual and would demand a search for star field contamination and for instrumental discontinuities. In each case, the unusualness is framed as a mismatch between channels. By the end of this region, the inquiry has crossed from descriptive measurement to physically oriented diagnosis while remaining cautious. The object's behavior is summarized as an evidence pattern, not as a story. The pattern either supports material release or constrains it. It either aligns with known regimes or presses against them. This prepares the next inward step, which focuses specifically on point source versus extended light in a more detailed way. Because the existent structure and evolution of any coma around 3I Atlas is the most immediate physical sign that can be extracted from imaging and that can anchor subsequent discussion of dust and gas processes without leaving the ground of what the data shows. With the first physical boundary crossed, the next region focuses tightly on the question of point source versus extended light, because this is often where an object transitions from being a simple moving dot to being a physical system interacting with sunlight. In this region, the inquiry is observationally concrete. It asks how extension is detected, how it is quantified, how it can be faked by the measurement process, and what the presence or absence of extension implies within stated limits. The phrase "behaving unlike any known object" is treated here as a claim about morphology, because morphology is where the physical reality of surrounding material becomes visible. A point source is defined operationally by comparison to stars. Stars are effectively points at astronomical distances. In any given image, the star's profile is shaped by the atmosphere and the telescope optics. This profile, the point spread function, has a core and wings. The core contains most of the light. The wings extend outward at low levels. A perfect point source would match this profile exactly. Therefore, the first test for extension is to measure the object's radial profile and compare it to nearby stars with similar brightness. Similar brightness matters because the detector response and noise properties can be brightness dependent. If the object is much fainter than the comparison stars, noise can broaden the measured profile. If the object is much brighter, nonlinearity and saturation can distort the profile. The best comparison uses stars close in brightness and close in position to the object in the same frame. The radial profile can be summarized in several ways. One is the full width at half maximum, the width of the profile at half its peak. If the object's full width at half maximum is consistently larger than that of nearby stars, this suggests extension. Another is encircled energy, the fraction of total light contained within a given radius. A coma tends to add light at larger radii, increasing the fraction of light outside the core. Another is a direct difference profile, subtracting the average star profile from the object profile after scaling the core. If residual light remains in the wings, a coma is indicated. Each method has sensitivities and weaknesses. Full width at half maximum is simple, but can miss faint halos that do not change the half maximum level much. Encircled energy is more sensitive to faint halos, but is more sensitive to background subtraction errors. Difference profiles can highlight weak extension, but can be biased by small miscentering. Centering matters because a coma is defined relative to the nucleus position. If the object is faint, the centroid can shift by fractions of a pixel between frames. When many frames are stacked, these shifts can broaden the object, creating artificial extension. Therefore, coma detection often uses careful centroiding and may exclude frames with poor centering. Some methods align frames on the stars to get a stable point spread function, then model the object's motion and measure its profile in individual frames rather than in a stack. Other methods align on the object and accept that stars trail using separate star stacks to measure the point spread function. In all cases, the key is to ensure that the profile comparison uses the correct reference and that alignment does not introduce spurious halos. Seeing variation is another critical factor. Seeing can change over minutes. If the object frames are taken during worse seeing than the frames used to measure star profiles, the object can appear broader. This is why star profiles must be measured from the same frames as the object. Even within the same frame, anisotropic seeing can produce slight elongation. Guiding errors can do the same. To address this, observers measure the shape of stars near the object. If stars show a consistent elongation in a particular direction, and the object shows the same elongation, it is likely a tracking or seeing effect. If stars are round and the object is elongated, it is more likely intrinsic, but only after checking for motion trailing. Motion trailing is especially relevant for a moving object. If the telescope tracks stars and the object moves during the exposure, the object trails. A trailed point source looks like a short streak, which can be mistaken for a tail if the streak points in a meaningful direction by coincidence. The length of the streak depends on the object's rate of motion and the exposure time. This is calculable. Therefore, in this region, one essential diagnostic is whether the measured elongation matches the predicted trailing length and direction. If it does, it is not a coma. If it does not, extension remains possible. Tracking on the object avoids this, but causes star trailing, which complicates the point spread function. Short exposures can reduce trailing for both approaches and allow more reliable shape comparisons. Once extension is detected, its brightness distribution can be measured. A classical steady-state cometary coma often shows a surface brightness profile that falls roughly inversely with projected distance from the nucleus under simple assumptions of constant outflow. Real comae deviate due to grain dynamics, photochemistry, and viewing geometry, but the general idea is that a coma has a gradual fall-off rather than an abrupt cutoff. Measuring the coma profile can indicate whether the extension is consistent with a physical outflow. Instrumental halos often have different patterns, such as a uniform gradient or a symmetric pattern around bright stars. If the object's extension follows a coma-like profile centered on the object, this supports a physical interpretation. If the extension appears as a uniform smear or an irregular patch that does not center on the object across frames, it is less convincing. Asymmetry within the coma provides additional constraints. A sunward fan suggests preferential release on the sunlit side. A tailward enhancement suggests dust being pushed away. A symmetric coma suggests more uniform activity or a low level where asymmetry is below detection. Yet asymmetry can also arise from background gradients and from subtraction errors. Therefore, in this region, the orientation of asymmetry is tested against the anti-solar direction and against the direction of motion. If asymmetry remains aligned with the anti-solar direction over time as geometry changes, this is consistent with solar-driven shaping. If it remains fixed in detector coordinates, it is likely an artifact. The presence of extension also interacts with photometry. If a coma is detected, total brightness can be decomposed into nucleus and coma components only with modeling. A simple approach is to assume the nucleus is a point spread function like core and subtract a scaled star profile, leaving the coma residual. This yields a nucleus brightness estimate and a coma brightness estimate. Yet the scaling can be uncertain if the coma contributes within the core. A more complex approach uses simultaneous fitting of a point source plus a coma model convolved with the point spread function. For faint targets, such modeling can be unstable. Therefore, in this region, the emphasis remains on qualitative and semi-quantitative results, whether a coma is present, whether it is weak or strong relative to the core, and whether its extent changes over time. If no extension is detected, limits are still meaningful. Observers can estimate the surface brightness threshold at which a coma would have been detected, given the noise in the background and the stacking depth. They can translate this into an upper limit on dust production under assumptions about grain properties and velocities. These assumptions introduce uncertainty, but the limits can still constrain extreme activity. A non-detection under deep imaging can rule out a bright, large coma. It cannot rule out a compact or gas-rich coma that is faint in broadband light. Therefore, in this region, absence of extension is framed as a limit within a defined sensitivity, not as proof of inactivity. If 3I Atlas is said to behave unlike any known object, one version of that claim could be that it shows extension in a form that is inconsistent with usual comet morphology. For example, an extended halo with no obvious tail alignment, or a tail that appears in the wrong direction, or an extension that changes too rapidly. Each would require careful verification. Another version could be that it shows no extension despite brightness trends, or orbital evidence suggesting activity producing a mismatch between channels. This mismatch, if real, becomes a key clue for later regions about gas-rich behavior, unusual dust properties, or extreme size and mass ratios. By the end of this region, the object is described in the most tangible terms, available point, like within measured limits, or extended with measured characteristics. The criteria for that description are explicit profile comparisons, encircled energy behavior stacking and alignment tests, and orientation tests against known geometric directions. This sets the stage for the next inward step, which examines tail geometry and alignment more fully, because once extended material is established, its large-scale direction and curvature become the next most diagnostic outward sign linking the near-nucleus environment to the forces of sunlight pressure and solar wind that sculpt material as it departs, and providing another place where an object can appear unlike known patterns if the geometry does not match the expected force frameworks. With the distinction between point source and extended light established, the next region turns outward along that extension into tail geometry and alignment. In this region, the emphasis remains on what the images show, but the geometry now becomes more structured, because a tail is not merely an aesthetic feature. It is a map of forces acting on released material. The most basic question is whether any elongated structure behaves in the ways known dust and ion tails behave under sunlight pressure and solar wind interaction. The phrase "behaving unlike any known object" becomes testable here, because tail direction and curvature are constrained by predictable vectors. If the structure aligns with those vectors, the behavior may still be uncommon in degree, but it sits within known physics. If it does not align, either the viewing geometry is producing a deceptive projection, the material release history is unusual, or the feature is not physical. The first geometric reference is the anti-solar direction. For any time in orbit, the Sun's position relative to the object is known. The anti-solar direction is the direction from the object pointing directly away from the Sun projected onto the plane of the sky. Ion tails formed from ionized gas that is coupled to the solar wind magnetic field tend to align close to the anti-solar direction because the solar wind sweeps ions away from the Sun. Ion tails can be narrow and straight. They can also show kinks and disconnections because the solar wind is variable. Dust tails, by contrast, are shaped by sunlight pressure and gravity acting on solid particles. Dust does not couple strongly to magnetic fields. Dust grains leave the nucleus with some initial velocity and then follow trajectories that depend on their size. Smaller grains are pushed more strongly by sunlight pressure relative to gravity. Larger grains are pushed less and remain closer to the object's orbital path. As a result, a dust tail is often broader and can be curved. Its average direction often lies between the anti-solar direction and the projected orbital direction, and that direction can change with time as different grain populations dominate. The second reference is the projected orbital direction. This is the direction of the object's motion on the sky, and more subtly, the direction of the orbit plane projected onto the sky. Dust released earlier can spread along the orbit, producing a dust trail that aligns more closely with the orbit path. Such trails can persist even when current activity is weak, because large grains released earlier can remain near the orbit for long times. In this region, distinguishing a tail from a trail matters, because a trail reflects older release history, while a tail reflects more immediate response to sunlight pressure. The distinction is made through geometry and through curvature. A trail tends to align closely with the orbit and can appear as a narrow structure. A dust tail influenced by sunlight pressure tends to bend away from the orbit and away from the sun. Yet projection can complicate this. A curved structure in 3 dimensions can project as straight, and a straight structure can project as curved depending on viewing angle. Detecting a tail for a faint object is a challenge of surface brightness. Tail light is spread out, so each pixel contains little signal. The standard strategy is to use deep stacking aligned on the object. This increases sensitivity to features fixed relative to the nucleus. However, tails can change over time. Dust features can evolve as particles move outward. Ion tails can change rapidly with the solar wind. If images are stacked over too long, an interval-changing features can smear, reducing contrast or creating an artificial broad structure. Therefore, in this region, observers often create stacks over shorter intervals and compare them, looking for consistent orientation. They may also apply image enhancement techniques, such as subtracting an azimuthal average coma to highlight directional features. Enhancement can reveal faint structures, but can also create artifacts if the underlying coma model is imperfect. Therefore, a feature is treated as credible only if it appears under multiple reasonable processing choices. Orientation measurement is then done with respect to the nucleus. Observers measure a position angle on the sky, the angle from north through east to the feature's direction. They compute the expected antisolar position angle and the expected projected orbital position angle at the same time. Then they compare. If the feature lies close to the antisolar angle, it is consistent with an ion tail or with very small dust grains dominated by sunlight pressure. If it lies closer to the orbital angle, it is consistent with a dust trail or with larger grains. If it lies between it, is consistent with a dust tail composed of a range of grain sizes and release times. If it lies outside these ranges persistently, the feature demands explanation. One possibility is that the feature is not a tail, but a jet within the coma close to the nucleus. Jets can point in directions that do not align with antisolar or orbital vectors because they reflect the nucleus rotation and vent geometry. Yet jets typically curve or broaden as they move outward and are often most visible near the nucleus. Another possibility is that the feature is an artifact such as a residual star trail or background gradient aligned with the stacking direction. Therefore, the region stresses that the spatial scale matters. Near-nucleus features are interpreted differently from far-tail features. Curvature is the next diagnostic. A dust-tail curvature can often be understood through syndine and synchrone concepts, which are geometric constructions used to model dust under sunlight pressure. A synchrone represents particles released at the same time with different sizes. A syndine represents particles of the same size released at different times. The pattern of these curves in the sky depends on the orbit and viewing geometry. In this region, these concepts are described in plain terms as time and size sorting. If a tail's curvature matches what is expected for plausible dust sizes released over plausible timescales, it supports a dust interpretation. If the curvature does not match any reasonable combination, the situation becomes unusual. Yet the region remains cautious because modeling requires assumptions and faint tails can be affected by processing. Therefore, curvature is used as supportive evidence rather than as definitive proof. Brightness distribution along the tail also provides clues. A tail that fades smoothly with distance is consistent with dispersing dust. Knots or segments can suggest time-variable release or dust fragmentation events. However, knots can also arise from background subtraction errors or from residual star streaks. A credible knot should move outward relative to the nucleus over time in a way consistent with dust motion. This can be tested by comparing images taken on different nights. Because the object moves across the sky, background stars do not remain in the same object-centered position, so persistent object-centered features are more likely physical. This is a key strength of moving object analysis. It allows background separation through repetition. If an ion tail is present, its behavior can be distinctive. Ion tails can be thin, straight, and sometimes show rapid changes. Disconnection events where part of the ion tail appears to detach can occur when the solar wind magnetic field changes. If such changes are observed, they can be evidence of ionized gas, though confirmation requires spectral detection of gas species and ideally narrowband imaging. In this region, the possibility of ion tail variability serves as a reminder that some tail behavior can be driven by external solar wind changes rather than by changes in the object itself. Therefore, a sudden change in tail appearance is not automatically an outburst. It can be a space weather effect. The phrase, "unlike any known object," could also be invoked if tail geometry implies a particle population or release history that is outside typical ranges. For example, an extremely bright tail at large heliocentric distance could imply unusually high dust production or unusual reflective dust. A tail dominated by very fine particles could show strong forward scattering and unusual brightness dependence on phase angle. A tail dominated by very large particles could remain close to the orbit and persist. None of these are impossible within known physics, but their combination with orbit class and brightness trends could be uncommon. The region therefore treats unusual tail properties as quantitative unusual length, unusual surface brightness, unusual alignment, evolution, or unusual persistence. By the end of this region, tail evidence is placed into a geometric framework. If a tail or trail is detected, its position, angle, curvature, width, and evolution are described and compared to antisolar and orbital directions. If no tail is detected, upper limits on surface brightness and extent are stated, which constrain dust production in a broad sense. The result then supports the next inward step, which turns away from geometry and toward the environmental driver that makes tails possible in the first place: sunlight heating. The inward path continues from tail shape to the energy balance at the surface, because the strength and timing of activity are ultimately controlled by how sunlight warms materials and how those materials respond, and it is at that boundary that the physical meaning of any observed unusual behavior begins to emerge in a controlled way. With tail geometry framed as a map of forces acting on released material, the inward path now turns to the driver that makes such release possible: sunlight heating. In this region, the focus shifts from the shape of what is seen to the conditions that can produce it. The sun delivers energy. The object absorbs, reflects, re-radiates, and conducts that energy. The balance sets surface and near-surface temperatures. Those temperatures determine whether volatile substances can turn into gas, whether trapped gases can be released, and whether dust can be lifted. The region remains general because it describes environmental physics that applies to any small body, while also showing how small differences in material properties and geometry can lead to very different observable behavior. This is where an object can appear unlike known objects, not because the physics is unknown, but because the combination of distance thermal history and accessible volatiles can place it in a rare regime. Sunlight intensity at the object falls with the square of distance from the sun. As the object approaches, the energy input increases rapidly. Yet surface temperature does not rise linearly with energy input, because the surface also radiates heat away as infrared emission. Radiative cooling increases strongly with temperature. Therefore, surface temperature is set by an equilibrium between absorbed sunlight and emitted heat, modified by how much heat is conducted into the interior and by how fast the surface rotates into and out of sunlight. A dark surface absorbs more sunlight and heats more. A bright surface reflects more sunlight and heats less. The angle of sunlight matters too. A patch facing the sun heats most. A patch near the terminator, the boundary between day and night, receives grazing light and heats less. This creates temperature gradients across the surface. If the object rotates, these gradients move, and each patch experiences a cycle. Rotation introduces a key parameter: thermal inertia. Thermal inertia describes how resistant the surface is to temperature change. A low thermal inertia surface, such as a porous dust layer, heats quickly in sunlight and cools quickly in shadow. This creates large day-night temperature swings and keeps heat near the surface. A high thermal inertia surface, such as more consolidated material, changes temperature more slowly and allows heat to penetrate deeper during the day and to be released during the night. The depth to which daily temperature variations reach is called the thermal skin depth. If volatile rich material lies deeper than this depth, it may remain stable and not respond strongly to daily cycles. If it lies within this depth, it can respond, producing diurnal variations in outgassing. In this region, the key point is that two objects at the same distance from the sun can have very different surface temperature histories and therefore very different activity thresholds. Volatile substances have different sublimation behaviors. Water ice sublimation becomes strong closer to the sun. Carbon dioxide ice and carbon monoxide ice can sublimate at lower temperatures and can drive activity farther out. There are also processes where gases trapped in ice are released as the ice changes structure. One important example is the transition of amorphous water ice to crystalline ice. Amorphous ice forms at very low temperatures and can trap gases. When it warms, it can reorganize into crystalline ice and release those trapped gases. This can produce gas outflow at distances where water sublimation alone might be weak. In this region, these processes are presented as general pathways through which heating can lead to gas release. The specific species and depths depend on the object's composition and history, but the physics of temperature-dependent phase change is established. The heating environment is not only about distance, it is about time. An object on a fast trajectory may spend only a limited time in the temperature range where certain volatiles become active. If the object is on an unusual orbit, the heating rate, meaning how quickly temperature conditions change, can differ from that of a typical periodic comet. A rapid change in heliocentric distance can mean a rapid change in surface energy input. Materials may not have time to equilibrate. Heat may not have time to penetrate deeply before conditions change again. This can produce lags and transients. For example, a volatile layer might begin to warm but not reach strong sublimation before the geometry changes. Conversely, a shallow, volatile pocket might cross its activation threshold quickly and produce a sudden change. In this region, unusual behavior is linked to heating rate as well as to distance. Illumination geometry also matters through the object's spin axis orientation. If the axis is tilted, some regions may receive more sustained sunlight, while others remain in prolonged shadow. This creates seasonal patterns even on a small body. If a particular hemisphere is illuminated strongly during the observing window, activity may appear localized and may change as the object rotates. If the active region moves into shadow, activity can drop. Because sublimation rates depend strongly on temperature, these changes can be sharp. Therefore, around any key date, the observed behavior can depend on whether the object's geometry places active regions into view and into sunlight. Without knowing, the spin axis predictions remain uncertain. Yet the region shows that geometry can explain apparent changes that might otherwise be called unusual. Heating also affects mechanical properties. Repeated thermal cycles can crack surfaces. Thermal stress arises because materials expand when heated and contract when cooled. Cracks can open pathways to deeper volatiles, increasing gas escape and dust lifting. Heating can also cause sintering, where grains fuse slightly, increasing cohesion and reducing permeability. Thus, heating can both open and close pathways. In some cases, dust can accumulate into an insulating mantle that reduces heat penetration, delaying activity. In other cases, heating can cause a mantle to fail, leading to an outburst. These processes can produce non-smooth behavior in brightness and morphology, even under smooth changes in distance. In this region, such behavior is framed as a natural outcome of a layered porous surface responding to increasing energy input. If gas release occurs, it can carry dust. Gas drag can lift grains if the upward force exceeds gravity and cohesion. Gravity on a small body is weak, but cohesion can be strong, especially for fine grains. Therefore, dust lifting can depend on both gas flux and grain properties. A gas-rich dust pore outflow can occur if gas escapes through pores without lifting much dust. A dust-rich outflow can occur if gas flow is strong enough and the surface is loose enough. The visible coma and tail depend strongly on dust, because dust scatters sunlight efficiently. Gas can be present yet produce a weak visible signature if its emission features are outside the observed bands or if the gas is not abundant enough. Therefore, an object can be active in gas but appear nearly point-like in broadband images. This is one way an object can appear unlike known objects if the usual coupling between heating gas release and visible dust does not occur, producing mismatched observational channels. The role of sunlight pressure and the solar wind also remains in view. Sunlight pressure shapes dust trajectories once dust is released. The solar wind shapes ion tails if gas is ionized. Both depend on the sun's output, which varies. Space weather events can alter ion tail appearance. Increased solar activity can change ionization conditions. These external factors can produce changes in tail morphology that are not due to changes in outgassing. In this region, the environment is therefore not only heating, it is also radiation and plasma interaction, which can modulate the appearance of released material. By the end of this heating region, the object's unusual behavior is framed as a response to a temperature history and an illumination geometry. If the object shows activity at a distance where typical water-driven comets are quiet, the region offers plausible drivers such as more volatile ices or trapped gas release. If it shows sudden changes, the region offers mechanisms such as mantle failure or rapid threshold crossing in shallow volatiles. If it shows weak dust despite potential heating, the region offers insulation or cohesion regimes. None of these are asserted as the case. They are the physics map that will guide the next inward step to surface layers and insulation, because the surface is where heating is translated into escape. The next region therefore examines the structure and evolution of the surface mantle and near-surface porosity in more detail, since these properties control whether heating produces smooth activity, episodic outbursts, or near invisibility in dust even when gas may be present. With sunlight heating described as the environmental driver, the next inward region focuses on surface layers and insulation, because the surface is the gatekeeper that decides how heating becomes observable activity. In this region, the object is treated as a layered porous body rather than as a simple solid. The surface is not static. It evolves as volatiles are lost, as dust is redistributed, and as stresses fracture or seal pathways. Many of the most puzzling behaviors in comets and active small bodies arise not from exotic energy sources, but from the way a thin surface layer can alternately block and release gases and dust. Therefore, an object can appear unlike known objects when its surface layer produces an uncommon combination of delayed onset, sudden bursts, weak dust coupling, or unusual persistence of activity. A common conceptual picture begins with a mixture of ice and dust. As the object warms, some ice sublimates and escapes as gas. The dust that was mixed with that ice does not evaporate. It can be left behind as a loose residue. Over time, this residue can accumulate into a mantle, a layer of refractory material at the surface. Refractory means it remains solid at the temperatures reached. The mantle can be porous, allowing some gas to percolate, or it can become compacted and less permeable. The mantle's properties depend on grain size distribution, on how dust settles, and on whether grains are cemented by residual ice or by sintering. In this region, the mantle is central because it can insulate underlying ice from sunlight and can reduce gas escape. An object can therefore warm externally while remaining quiet, because the insulation prevents heat from reaching volatile layers and prevents gas from escaping efficiently. Insulation is not only thermal, it is also hydraulic in the sense of gas flow. A mantle with low permeability acts like a cap. Sublimation below the cap can build pressure. If gas cannot escape easily, it can accumulate in pores and fractures. Pressure rises until gas finds a path such as a crack or a weak spot, or until the cap fails. When it does, an outburst can occur, releasing gas and dust suddenly. Outbursts can produce rapid brightening and can create expanding shells or jets. In this region, outbursts are not treated as rare miracles. They are a natural outcome of a system where gas production increases with temperature, but is throttled by a variable permeability layer. The mantle is also shaped by gravity and cohesion. On a small body, gravity is weak. Dust grains can be moved by gentle forces. Gas flow can loft grains and then allow them to fall back if they are not accelerated beyond escape velocity. This fallback can thicken the mantle. Electrostatic forces can also mobilize fine grains, causing them to migrate and settle. Over time, this can lead to a surface that is patchy, with some areas covered by a thick insulating layer and other areas thinner or exposed. Patchiness can produce localized activity where only certain regions vent. This can create jets and asymmetric como. It can also create a behavior where the object appears inactive most of the time, but occasionally shows activity when an exposed patch comes into sunlight or when a vent opens. The structure of the mantle matters for dust coupling. Gas escaping through a thick mantle may emerge through narrow pores. The gas can escape without lifting much dust if the pores are small and if grains are held by cohesion. This can produce gas-rich dust, poor activity, where the object may show non-gravitational acceleration or gas emissions, but little visible dust coma. Conversely, if the mantle is thin and loose, gas can lift fine grains, easily producing a dust-rich coma and tail. Therefore, in this region, a mismatch between evidence channels can be explained by mantle properties. An object can be physically active but visually quiet in dust. An object can show dust without strong gas lines if dust is released mechanically by surface shedding or by weak gas that is hard to detect spectroscopically. Thermal cycling can change the mantle. Day-night temperature swings can cause expansion and contraction that cracks the surface. Cracks increase permeability and expose deeper material. Yet cracks can also become filled by redeposited dust or by recondensed volatiles resealing them. Recondensation can occur when gas flows from warm regions into cooler regions and freezes out. This can create a cement that binds grains and increases cohesion. Therefore, the mantle can self-organize into a dynamic system that alternates between open and sealed states. This can produce repeated activity cycles or bursts. In this region, such behavior is not attributed to unknown physics. It is attributed to a thin boundary layer that is sensitive to small changes in temperature and stress. Another near-surface process is the crystallization of amorphous ice and the release of trapped gases. If amorphous ice exists below the surface, heating can trigger its transformation, releasing gas. That gas can move through pores and contribute to pressure buildup. It can also alter the mantle by lifting grains or by widening cracks. The transformation also releases latent heat, which can locally increase temperature and accelerate nearby processes. In this region, the crystallization process is treated as a potential contributor to sudden changes, especially at distances where water sublimation alone would be modest. If 3I Atlas shows activity onset earlier than expected, a surface layer that preserves amorphous ice or highly volatile ices could be a plausible mechanism, especially if the object's thermal history has kept it cold for long times. Surface composition also affects insulation. A mantle rich in very fine grains can be a strong insulator because fine grains trap airless voids and reduce thermal conductivity. A mantle rich in coarse grains can be less insulating and more permeable. The presence of dark organics can increase absorption and raise surface temperatures, which can increase sublimation rates, but can also promote sintering or crust formation. The presence of ice within the mantle can increase thermal conductivity and cohesion, changing the balance. Therefore, in this region, the surface is a set of coupled properties rather than a single parameter. These surface processes can produce behavior that seems unlike known objects when the timing and degree are uncommon. A strong mantle can delay activity, making an object appear inert until a sudden outburst. A patchy mantle can produce intermittent jets that change with rotation. A dust-poor vent can produce gas signatures without a prominent dust coma. A dust-rich mantle failure can produce a bright dust cloud with weak gas lines. Each outcome is familiar in parts of the comet population, but the combination with a particular orbit class and observation geometry can be rare. For an object with an unusual trajectory, the surface may not have been pre-processed by repeated perihelion passages. This can change mantle development. A first-time heating event can produce a different sequence of sealing and failure than a repeatedly processed comet. In this region, this is presented as a reason why the object's behavior might fall outside common patterns, while still being explainable through known surface physics. The end of this region sets up a more specific inward test. Surface layer models predict different balances between gas and dust and different spectral signatures. If gas escapes without much dust, spectroscopy may show emissions while imaging remains point-like. If dust is released strongly, imaging shows a coma and tail and color may redden. If outbursts occur, time-resolved imaging can show expanding structures. Therefore, the next inward region turns to gas signatures in spectra, because spectra can test whether gas is present and which kinds, and thereby constrain whether observed dust features are driven by sublimation, by trapped gas release, or by mechanical shedding. Spectral evidence becomes the most direct bridge between surface layer behavior and physical composition. And it is the channel that can either anchor or refute interpretations that rely only on imaging and brightness trends. With surface layers framed as the gatekeeper that can either reveal or hide activity, the next inward region turns to gas signatures in spectra, because gas is the most direct chemical evidence available at distance. Dust can be lifted mechanically, and dust can scatter light without telling which volatile drives it. Gas, when detected through characteristic emission or absorption features, provides a clearer link to processes at and below the surface. Yet spectroscopy is also one of the most demanding measurements for a faint moving target. A spectrum is not a photograph. It is a redistribution of light into many narrow wavelength bins, which lowers signal in each bin and raises sensitivity to background subtraction and calibration errors. Therefore, this region focuses on what spectral measurements can show reliably how detections and non-detections are interpreted, and how unusual behavior claims are strengthened only when spectral evidence is both repeatable and consistent with the imaging and dynamical context. The baseline spectral signal for a passive small body is reflected sunlight. In visible and near-infrared wavelengths, the sun's spectrum provides the illumination. When sunlight reflects from a surface or dust, the result is a solar spectrum multiplied by the reflectance of the material. In practice, this produces a continuum that carries the overall slope and broad features of the material while retaining the fine absorption lines present in the solar spectrum. For analysis, observers often remove the solar imprint by dividing by a solar analog star, producing a reflectance spectrum that emphasizes the object's own wavelength dependence. In this region, the key point is that a continuum-dominated spectrum is not evidence of inactivity. It is simply evidence that emission lines, if present, are below detection or outside the observed range. A dusty coma can also produce a continuum because dust mainly scatters sunlight. Therefore, the presence of a smooth continuum can be consistent with both an inert nucleus and a dust-rich active coma. The distinction then depends on spatial information and on the presence of subtle emissions. Gas becomes visible spectrally because molecules and molecular fragments emit or absorb light at specific wavelengths. In cometary environments, many observable gas features in the optical come from radicals produced when parent molecules are broken apart by sunlight. Ultraviolet photons drive photodissociation, creating fragments that can fluoresce absorbing sunlight and re-emitting at characteristic bands. Some of the most commonly used optical tracers include CNs and C2, which produce band systems that can be detected in sufficiently active comets. These are not usually direct measures of bulk composition. They are indicators of accessible chemistry and of photochemical pathways in the coma. In the near-infrared signatures of water carbon dioxide and carbon monoxide can be detected in favorable conditions. However, Earth's atmosphere absorbs strongly in parts of the infrared, especially due to water vapor, and this can limit ground-based detection. Space-based observations can avoid much of this absorption and can provide cleaner access to key bands. Therefore, a spectral campaign often combines ground-based optical spectroscopy with infrared observations when possible. The first practical challenge is the sky background. Night sky emission includes many narrow lines and broad components that vary with time. For faint targets, these can dominate the signal. Spectral reduction must subtract the sky accurately. This is typically done by measuring the sky in regions of the slit or field adjacent to the target and subtracting it. For a moving target, the target may drift slightly, and the sky subtraction regions may include faint stars or gradients. Residual sky lines can remain and can mimic emission features. Therefore, robust gas detection requires that a feature persist under different reduction choices appear at the expected wavelength after correcting for the object's Doppler shift and be present across independent observations. The Doppler shift is important because the object moves relative to Earth. Spectral lines and bands shift slightly. A real cometary emission feature should track that shift, while many instrumental or sky features remain fixed in the observer frame. This provides a powerful discriminant in this region when data quality allows it. Telluric absorption is another major challenge. Earth's atmosphere produces absorption bands that can distort spectra. Correcting these requires observing standard stars at similar air mass and dividing by their spectra. If the atmosphere changes rapidly, residuals remain. In some cases, a residual telluric band can resemble a broad absorption feature from the object. Therefore, claims of unusual absorption bands require careful validation, including checks that the feature does not correlate with air mass or water vapor, and that it appears in data from different nights or sites. For emission features, telluric absorption can also suppress or reshape lines, making quantitative measurement uncertain. In this region, a cautious approach emphasizes detection significance and repeatability more than precise abundance ratios unless the data quality is high. Spectral measurements also depend on spatial sampling. A long slit spectrum collects light along a narrow line. If a coma is present, the slit may include different fractions of it depending on slit width, seeing, and guiding. A narrow slit can lose light due to seeing and guiding errors, a problem known as slit loss. Slit losses can change the continuum level and can change the apparent strength of emission features relative to continuum. If the coma is asymmetric, slit orientation matters because one orientation may capture a jet while another misses it. Therefore, in this region, spectral interpretation benefits from accompanying imaging that shows coma shape and from documentation of slit width, position, angle, and tracking mode. When possible, observers compare spectra extracted from the nucleus region to spectra extracted from regions offset along the slit to see whether emission is extended. Extended emission supports a coma source. A feature confined to the nucleus extraction could be a surface reflectance feature, or could be a localized gas source tightly bound to the nucleus region. When emission is detected, the next step is to interpret it as a constraint on gas production. The conversion from measured line flux to production rate depends on fluorescence efficiencies and on the outflow velocity and lifetime of the species. These quantities vary with heliocentric distance and with solar activity. They are known approximately from comet studies, but they carry uncertainties. Therefore, production rates are usually reported with uncertainty ranges and with assumptions stated. The most stable use of a detection in this region is comparative. If the production rate of a tracer rises with decreasing distance, it supports heating-driven activation. If it remains constant, it may suggest a stable reservoir or a measurement limitation. If different species behave differently, it may suggest a change in which volatile dominates, or a change in coma chemistry. Yet even these patterns must be interpreted cautiously, because the detectability of different species can change with observing setup, and because photochemistry can alter relative abundances with distance from the nucleus. Non-detections can be as informative as detections when they are deep. A non-detection is converted into an upper limit on line flux and then into an upper limit on production rate under assumed conditions. Upper limits narrow the space of possible activity regimes. If a coma is visible in broadband images, but gas lines are not detected to strong limits, the coma may be dust-dominated with low gas to dust ratio, or the dominant gas species may be one not well traced by the observed lines. If a non-gravitational acceleration is suggested by orbit residuals, but gas lines are not detected to strong limits, then either the gas is released in a species not measured, the production is low but still sufficient to create thrust for a low-mass object, or the acceleration inference may be affected by photocenter bias. In this region, the power of spectroscopy is that it can help distinguish between dust-driven appearance and gas-driven forces, but it rarely resolves all ambiguity alone. There is also the possibility of gas signatures that are not in emission. In some cases, absorption features in the near-infrared can indicate ices or certain minerals, especially if the nucleus surface is exposed. Detecting such features requires that the nucleus contribute a significant fraction of the light and that the signal-to-noise be high. If a coma dominates absorption, features can be diluted. If the surface is dark and featureless, absorption features may be weak. Therefore, absence of absorption features does not rule out ices. It can mean that ices are below a dust layer or present at low surface fraction. Conversely, a clear detection of water-ice absorption bands would be strong evidence for exposed ice, which would connect directly to surface layer models and to heating thresholds. In this region, such detections are treated as rare but decisive when confirmed. Spectroscopy can also test for temporal changes that align with reported unusual behavior. If an object shows a sudden brightening event, spectra taken before and after can test whether gas emission increases, whether the continuum slope changes, and whether new features appear. An outburst driven by gas release might show increased emission and perhaps a change in relative species. A dust-dominated shedding event might show a stronger continuum without a commensurate rise in gas lines. A fragmentation event might increase continuum and alter the spatial distribution of light without necessarily changing gas composition. These are tendencies rather than rules, but they provide structured ways to interpret combined data without overreaching. In the context of behaving unlike any known object, spectral results can either bring the object back into known regimes or push it toward rarer corners. If the spectrum shows typical cometary emissions and a typical dust continuum slope, then unusualness may lie mainly in orbit class timing or degree, rather than in chemistry. If the spectrum shows emissions at unexpected distances or unusual relative strengths that persist under careful calibration, then the accessible volatile inventory may be uncommon. If the spectrum remains largely continuum with strong upper limits on common gas tracers, while other channels suggest activity, then the object may occupy a less common regime of gas species, dust dominance, or mass-related dynamical sensitivity. The important feature of this region is that it anchors discussion in what is explicitly measured at particular wavelengths and sensitivities. By the end of this region, the spectral picture is expressed in concrete terms, which wavelength ranges are observed, what signal-to-noise is achieved, which features are detected with significance which are not detected with stated upper limits, whether emission is spatially extended, and whether features vary with time. These results then feed the next inward step, which examines non-gravitational motion tests more directly, because the presence or absence of gas and the inferred production rates provide the physical context needed to interpret any trajectory deviations. If gas is detected, non-gravitational acceleration becomes more physically plausible and can be used to constrain mass and asymmetry. If gas is not detected to strong limits, non-gravitational claims demand tighter scrutiny and alternative explanations. The inward path continues by letting motion constrain cause using the chemical and morphological context now established. With spectral signatures framed as direct evidence or direct limits on gas release, the next inward region returns to motion in the most diagnostic way available from afar non-gravitational motion tests. Here, the orbit is not only a classification tool. It becomes a probe of physical forces acting on the object. A small, sustained force can alter the trajectory in a measurable way, and for small bodies, the most plausible sustained force is asymmetric outgassing. The thrust from escaping gas depends on how much gas is released, how fast it leaves, and how asymmetrically it is directed over time. This region therefore connects the chemical and morphological evidence to dynamical behavior and asks whether the data require an extra force beyond gravity, and if so, what that force implies, about the object's mass and activity regime. Because astrometry can be extremely precise, this region can sometimes constrain activity even when imaging and spectroscopy are ambiguous. Yet it is also vulnerable to a specific confounder photocenter bias caused by asymmetric comae. Therefore, the region proceeds carefully using tests that distinguish true acceleration from measurement artifacts. A non-gravitational acceleration is inferred when a gravitational orbit model fails systematically. The measured positions differ from predicted positions in a way that is not random and that grows over time. The pattern can be seen in the residuals of the orbit fit. If the residuals cluster in one direction or drift with time, the model is missing something. Adding a non-gravitational acceleration term can improve the fit. The term can be expressed as components along directions tied to the orbit radial away from the Sun transverse, along the direction of motion and normal out of the orbital plane. These components are not arbitrary. They correspond to how physical thrust would project onto the orbit frame. Outgassing-driven thrust often has a significant radial component because the sunlit side tends to be more active, but thermal lag and rotation can introduce transverse components. Normal components can arise if active regions are not symmetric about the equator, or if the spin axis is tilted relative to the orbital plane. The standard cometary approach often assumes that the thrust magnitude varies with heliocentric distance in a way that resembles the sublimation rate of water ice. This provides a physically motivated distance dependence with stronger thrust nearer the Sun. For objects driven by more volatile species, the distance dependence could differ. Therefore, in this region, the fitting is done in a way that remains agnostic where needed. One can test whether any extra acceleration is needed at all before assuming a particular functional form. If data quality is high, one can also compare whether a water-like dependence fits better than alternative dependences. Yet the region emphasizes that the simplest robust outcome is detection or non-detection within stated confidence, plus an estimate of the magnitude of any detected acceleration. If an acceleration is detected, it can be used to infer a relationship between outgassing and mass. The thrust equals mass times acceleration. If gas production is estimated from spectra, and if the gas outflow velocity is estimated from typical comet values adjusted for distance, then one can estimate the expected thrust. Comparing that to the measured acceleration gives a constraint on mass. If the required mass is very small, it could imply a small nucleus or low density. If the required mass is large, it could imply a larger nucleus or less efficient thrust, because outgassing is more symmetric. Yet each input carries uncertainty. Gas production estimates may miss dominant species. Outflow velocities are not measured directly in many cases. The thrust efficiency depends on jet collimation. Therefore, in this region, the mass inference is treated as a range, not a single number. Even so, it can be powerful because it ties together independent channels and can rule out extreme combinations. If no acceleration is detected, upper limits can still constrain activity. For a given assumed mass range, an upper limit on acceleration sets an upper limit on the net thrust. That in turn sets an upper limit on the degree of asymmetry in outgassing for a given total production rate. If imaging or spectra suggests some level of activity, the absence of acceleration can imply that activity is relatively symmetric, producing little net thrust. Alternatively, it can imply that the nucleus mass is large enough that the same thrust produces too small an acceleration to detect. Or it can imply that the activity is dust-dominated with low gas thrust. Therefore, in this region, non-detection is not a blank result. It is a boundary condition that must be consistent with the other evidence. The confounder that must always be addressed is photocenter bias. If the object has an asymmetric coma, the measured center of light can shift away from the nucleus. This shift can change with viewing geometry and with activity producing apparent positional offsets that mimic acceleration. For example, if a tailward coma makes the photocenter appear shifted away from the sun, astrometric residuals could show a systematic pattern that looks like radial acceleration. The magnitude of such shifts can be a significant fraction of an arcsecond for faint comets in modest resolution images. Therefore, in this region, the most trustworthy non-gravitational detections come from astrometry that measures the nucleus position directly, such as high-resolution imaging, where the nucleus can be separated from coma, or from techniques that fit the inner coma symmetrically to locate the nucleus. Another trustworthy approach is to compare residual patterns from different observatories with different pixel scales and different seeing. If the residual pattern is consistent across data sets with different coma biases, it is more likely real. If it varies strongly with seeing or with aperture, it is more likely photocenter bias. There is also the possibility of radiation pressure affecting the nucleus if the object has an unusually high area-to-mass ratio. Radiation pressure is the force exerted by sunlight itself. It is important for dust grains and small fragments. For a normal nucleus-sized body, it is negligible compared to gravity. However, if the object were extremely low density or thin radiation pressure could be more relevant. This is an unusual regime, and this region does not assume it. It recognizes it as a theoretical alternative that would require strong evidence such as an acceleration direction that matches sunlight pressure expectations and cannot be explained by outgassing combined with other properties that imply low mass for the observed brightness. In most practical cases, outgassing remains the primary candidate for non-gravitational forces. Timing matters. Detecting a small acceleration requires time for its effect to accumulate and requires a long enough observation arc. An observing window can improve this by increasing the precision and frequency of astrometry near the time when the object is brightest and when it is closest. The same acceleration produces a larger angular deviation when the object is close, because a given linear displacement projects to a larger angle. Therefore, the period of best visibility can be crucial for detection. In this region, the role of a key window is to provide dense, high-quality positional data that allows residual patterns to be distinguished from noise and outliers. If 3-eye atlas is called unlike any known object, a dynamical mismatch is one of the most compelling versions of that claim. For example, a strong acceleration that cannot be reconciled with observed gas production or dust activity could be puzzling. A detected acceleration with a direction or distance dependence unlike typical comets could suggest an unusual outgassing species or a different thermal response. A lack of acceleration, despite strong apparent activity, could suggest symmetric outgassing or a large mass. Yet each of these must be kept within the logic of uncertainty. The region's function is to convert surprise into constraints that can be checked. By the end of this region, the dynamical picture is expressed as one of three outcomes with nuance. Either a non-gravitational acceleration is detected with magnitude direction and uncertainty, and with caveats about coma bias addressed. Or no acceleration is detected, and upper limits are stated with implications for activity and mass framed as conditional ranges. Or the data are inconclusive because residuals are dominated by systematic measurement issues, in which case the limitation is described explicitly. This prepares the final inward step, which gathers the layered evidence into a clear statement of what can be concluded and what remains uncertain, and which identifies which kinds of observations most efficiently reduce the remaining uncertainty. The final region stays close to the innermost scale that can be inferred from afar by emphasizing evidence boundaries rather than declarations, maintaining the calm constraint that the format requires. In the innermost region, the work becomes a calm accounting of what the layered evidence can support and what it cannot. The title statement that 3I Atlas is behaving unlike any known object becomes at this point a set of measured claims with boundaries. Each boundary is defined by sensitivity, by calibration stability, and by the agreement between independent channels. The object itself remains at a distance. It cannot be touched. It cannot be sampled. It cannot be resolved into surface features in most telescopes. Yet the combination of orbit refinement, photometry, color, morphology, spectroscopy, and motion tests can still narrow the range of plausible physical states. The value of the innermost region is not certainty. It is constraint. The first firm outcome that can emerge is a clarified trajectory and class. With sufficient astrometry over time, the orbit becomes stable. The eccentricity and its uncertainty range can be stated. The incoming direction and speed relative to the Sun can be computed. If the orbit remains robustly unbound after careful weighting and after re-reduction with modern star catalogs, the classification as interstellar becomes a strong statement about dynamics, not about appearance. If the orbit moves toward a bound solution as uncertainty shrinks, the classification becomes a different kind of story, but still one grounded in orbital mechanics. Either way, the trajectory becomes the reference frame for all other measurements, because it fixes distance, phase, angle, evolution, and observing geometry, and it allows different observatories to compare results on a common timeline. The second firm outcome is the brightness behavior once geometry is modeled. A calibrated light curve tied to a consistent photometric system and corrected for distance and phase effects, as well as possible, can show whether the object follows a passive reflector baseline or departs from it. If it follows the baseline within uncertainties, then claims of unusual brightening or fading soften into a statement of ordinary geometric behavior with the caveat that low-level activity could still be present below detection thresholds. If it departs from the baseline in a way that is replicated across instruments and nights, then an intrinsic change is indicated, and the nature of that change can be constrained by whether it is smooth, periodic, or abrupt. Smooth excess brightening is consistent with gradually increasing scattering area from an evolving coma. Periodic modulation is consistent with rotation-driven brightness changes and can constrain rotation period. Abrupt steps can indicate outbursts, fragmentation, or rapid activation of a new region, though they require careful exclusion of contamination and method discontinuities. The third firm outcome is whether extended light is present within stated limits. Deep imaging with robust point spread function comparisons can determine whether 3I Atlas is point-like or surrounded by a coma at the sensitivity achieved. If a coma is detected, its radial profile and asymmetry provide constraints on dust production and on directionality. If a tail is detected, its alignment and curvature provide constraints on dust size distribution and release history, and can indicate whether an ion component is plausible. If no extended light is detected, the resulting surface brightness limits constrain dust production in a broad sense, and can indicate whether any activity must be dust-poor or extremely compact. This morphological outcome is central because it anchors physical interpretation without requiring detailed chemistry. It states in the plainest way available whether material around the nucleus is visible. The fourth firm outcome is the spectral constraint. If gas emission features are detected with repeatability and with adequate calibration, they confirm active release of specific molecules or fragments, and they set production rates within stated assumptions. If multiple species are detected, their relative strengths can indicate which volatile reservoirs are accessible in the observed interval. If no features are detected, upper limits can be set. These upper limits can either be weak, leaving much open, or strong enough to rule out high production rates of common tracers. In either case, spectroscopy adds specificity. It can show whether activity is gas-rich or dust-dominated, and it can test whether unusual behavior claims are rooted in chemistry or mainly in dynamics and morphology. The fifth firm outcome is whether the motion requires non-gravitational forces. If orbit residuals cannot be explained by measurement errors and show a consistent pattern that improves with the inclusion of non-gravitational terms, then a net acceleration is indicated. If the acceleration is detected, its magnitude and direction can be compared to morphology and spectroscopy to assess plausibility and to constrain mass and asymmetry. If the acceleration is not detected, upper limits constrain the combination of thrust and mass and can indicate that any outgassing is either weak symmetric or acting on a relatively massive nucleus. In this innermost region, the dynamic constraint is treated as one more boundary line powerful when it aligns with other evidence and cautious when it stands alone. From these outcomes, the claim of unlike any known object becomes a statement about combinations. An object can be dynamically interstellar, yet physically ordinary in its surface properties and activity appearing similar to known comets or asteroids when placed in the same thermal regime. An object can be dynamically ordinary, yet physically unusual in its activity timing, such as showing strong activity at a distance where similar objects are quiet. An object can show mismatched channels, such as strong dynamical evidence for thrust with weak dust signatures, or strong dust signatures with weak gas signatures. Such mismatches are where the claim of unusual behavior becomes most meaningful because they indicate that the object sits in a less common part of the parameter space of small body behavior, shaped by surface insulation, volatile accessibility, and mass. Yet the innermost region also describes what remains uncertain. Size can remain uncertain without thermal infrared detection because reflectivity is unknown. Mass can remain uncertain without a combination of size and non-gravitational acceleration constraints. Composition can remain uncertain because spectra may cover limited bands and because coma chemistry reflects accessible reservoirs rather than bulk interior. Internal structure can remain uncertain unless fragmentation or rotation changes provide strong evidence. Even if many channels are measured, multiple models can remain compatible, especially when signal is faint and when the object is observed over a limited arc. Therefore, the most honest end state after a strong observing effort is a tightened map. A range of sizes consistent with brightness and any thermal data. A range of activity levels consistent with coma detection, or limits a set of detected or constrained gas species, a set of tail geometry measurements if present, and a statement about whether extra forces are required in the orbit. This map is valuable because it guides the next observations. If a coma is present, time resolved, imaging becomes the efficient next step to test for repeating jet patterns and to constrain rotation. If gas is detected, broader wavelength spectroscopy becomes efficient to capture additional species and to test how ratios change with distance. If non-gravitational acceleration is detected, continued astrometry becomes efficient to refine its distance dependence and direction. If the object remains point-like with strong upper limits, deeper spectroscopy and thermal observations become efficient to test for hidden gas-rich activity and to constrain size. In this innermost region, the narrative remains calm because it treats knowledge as bounded. The object's behavior is not forced into a single sentence. It is described as a set of constrained properties that either fit within known frameworks or occupy a rarer combination. That is the clearest meaning the evidence can carry without exaggeration. The sky provides the data. The method provides the limits. The result is a quiet, precise description of what is seen and what remains open, held steady, as the object continues along its path, and as the measurement record continues to accumulate. The night slows into a steady interval of recorded light, where the object's motion and the instrument's limits remain the only guides. The data taken across different hours and sites settle into a single timeline, and the timeline becomes the simplest kind of story positions that tighten an orbit. Brightness points that trace a curved spectra that either show lines or do not, images that either reveal faint extension or keep the object star-like. The meaning of behaving unlike any known object in this final quiet phase is reduced to what is repeatable. Anything that appears once is treated as fragile. Anything that appears again under different air, different detectors, and different reductions gains weight. The work becomes a practice of comparison. Frames from one night are aligned against frames from another. Brightness measurements from one facility are converted and placed next to those from another. A claimed tail is checked against the anti-solar angle, and the projected orbit direction again and again. A claimed emission feature is checked against the Doppler shift and against the sky subtraction residuals again and again. Repetition does not create novelty. It creates reliability, and reliability is the only path toward describing something as genuinely unusual. If the object proves to be point-like in the deepest stacks, the absence of a visible coma is held as a measured limit, not as a declaration of inertness. The limit belongs to a specific surface brightness threshold, reached under specific sky conditions. It implies that any dust production, if present, must fall below that threshold, or be confined so close to the nucleus that it cannot be separated from the point spread function. Under that constraint, attention naturally turns to whether any faint gas emission can still be present, because gas can escape without carrying much dust. If spectra show no lines down to strong limits, the space of plausible activity narrows further, and the object's oddness, if it remains, must lie elsewhere, perhaps in orbit class or in subtle dynamical residuals. If spectra do reveal gas lines while images remain point-like, then the object occupies a regime that is not impossible, but is less commonly seen in the public imagination activity, that is real yet visually quiet, with thrust and chemistry potentially present, while dust scattering remains weak. In that case, the simplest explanation is not a new law of physics, but a surface layer that allows gas to leak while holding grains down, a permeability and cohesion regime that can exist on small bodies, and that can be preserved if the surface has not been repeatedly processed by close solar passes. If the object shows a coma and perhaps a tail, the quiet ending holds that evidence as a map rather than as spectacle. The coma profile becomes a constraint on production and dispersion. The asymmetry becomes a constraint on where and when material leaves the surface. The tail direction becomes a constraint on whether dust ions or both dominate. If the tail aligns near the anti-solar direction and changes rapidly, space weather can be part of its appearance, and the object's intrinsic activity cannot be inferred from tail shape alone. If the tail curves and leans toward the orbit direction, dust size sorting and release history become more relevant. If the coma shows jets that repeat with a stable period, rotation becomes constrained. If the coma shows shells that expand between nights, outburst timing becomes constrained. In all cases, the work remains within the evidence. The patterns are described as they are seen, and as they persist without being turned into claims that go beyond the record. If a non-gravitational acceleration is detected, the ending holds it as a measured drift that has a physical interpretation, but also a required caution. The acceleration implies a net force, and outgassing is the most plausible source. Yet the possibility of photocenter bias must always be addressed. The most persuasive case is one where the acceleration persists across many data sets and where morphology and spectra provide consistent context. Under those conditions, the acceleration becomes a way to connect the microscopic act of gas escape to the macroscopic path through the sky. It can then constrain the product of mass and thrust, and with other constraints, it can narrow the likely mass range. If no acceleration is detected, the ending treats that as a boundary line. It limits the net thrust, and therefore limits how strong and how asymmetric any outgassing can be, unless the object is massive enough that the same thrust produces an undetectable effect. This again is not a conclusion about what the object is. It is a constraint on what it can be, while remaining consistent with the measured path. As the observations settle, the most practical sense in which an object can be unlike known objects is by occupying a rare combination of constraints. A strongly unbound orbit combined with a chemically ordinary spectrum and an ordinary dust coma would be rare in occurrence, but not strange in behavior. A strongly unbound orbit combined with an absence of visible dust and a lack of detectable gas would be rare in a different way, because it would offer fewer physical handles leaving the orbit as the primary certainty and leaving surface properties largely unconstrained. A mismatch between dynamical evidence and spectral evidence would be rarer still and would demand the greatest care because it could arise from subtle biases as easily as from true physical differences. The quiet ending does not choose between these possibilities. It places them on the same level of conditionality, allowing only what the data supports. The last settling of the narrative is a return to the simplest picture, a small body in sunlight moving on a trajectory that is now better defined than it was at discovery. The field stars remain fixed. The object advances from night to night. Each new observation either confirms a pattern or reduces a claim. The unusualness, if it survives, survives because it persists after noise geometry and method have been stripped away. If it does not survive, what remains is still valuable. A refined orbit, a measured light curve, spectral limits, and imaging limits, all of which add to the catalog of how small bodies behave under sunlight. In either case, the work ends not with a final interpretation, but with a calm inventory of what is known and what remains open, held steady in the same slow tone as the sky itself.